The solar system ends twice. Once at Neptune, where the familiar planets stop, and again 4.5 billion miles further out, where something vast and frozen begins. We call it the Kuiper Belt, and in 2024, NASA discovered it might be far larger than anyone ever imagined. For decades, we treated this region like a junkyard, a ring of ice and rock left over from the birth of the Sun, interesting only because Pluto happened to live there. We had a model, we had measurements, we thought we knew where it started and where it ended. And then New Horizons flew past a tiny frozen world called Arrokoth, and the dust counter kept ticking. Long after it should have gone quiet. Long after the belt was supposed to thin out and disappear into empty space, the signal didn't stop. It kept detecting particles, faint but persistent, streaming in from distances our models said should be barren. Which means one of two things. Either our instruments are lying, or the Kuiper Belt extends far deeper into the void than we ever believed possible. This is not a place where things make sense. Out here, dwarf planets have beating hearts made of frozen nitrogen. Ancient snowmen drift untouched since the dawn of time, and something massive, something we have never seen, may be pulling on the orbits of distant worlds from the shadows beyond. In 2026, if the predictions hold, we may confirm the existence of an atmosphere on a body so small and so cold it has no right to hold one. An impossible sky hanging over an impossible world, in a region of space we are only now beginning to understand. This is the story of the Kuiper Belt, the place where our solar system stops feeling like home and starts feeling like an abyss. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. For most of human history, the solar system had edges we could see. There was Earth, obviously, then the wandering lights in the sky that turned out to be other worlds, Mercury, Venus, Mars, then the giants, Jupiter, Saturn. Uranus showed up in 1781 when William Herschel pointed a telescope at what he thought was a comet and realized it was moving wrong. Neptune followed in 1846, predicted mathematically before anyone laid eyes on it, dragged into visibility by the gravity it was exerting on Uranus from the outer dark, and then for a long time, that was it. Neptune sat at roughly 30 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. 30 times that distance and you hit Neptune, a cold blue sphere with winds that scream faster than the speed of sound, orbiting in near silence at the edge of what anyone in the 19th or early 20th century would have called the solar system. Beyond Neptune, there was supposed to be nothing, empty space, the long slide into the void between stars. Textbooks drew the solar system as a neat row of planets with Neptune as the final bookend, and that picture held for decades. It felt complete. It felt finished. We had found all the planets. We had mapped the neighborhood. The frontier was closed, except it wasn't. Because even as Neptune was being discovered, astronomers noticed something strange. Neptune's orbit was behaving itself, more or less. But there were other oddities in the outer solar system that didn't quite add up. Objects were moving in ways that suggested there was more mass out there than anyone could see. The gravity wasn't balancing the way it should. Percival Lowell, the same astronomer who spent years convinced he saw canals on Mars, became obsessed with the idea that there was another planet lurking beyond Neptune. He called it Planet X. Not because it was mysterious, though it was, but because X was the algebraic symbol for an unknown. He spent the last years of his life searching for it, calculating where it should be based on perturbations in the orbits of Uranus and Neptune, aiming telescopes at patches of sky where the math said something heavy ought to be hiding. He never found it. He died in 1916, and the search continued without him. In 1930, a young astronomer named Clyde Tombaugh, working at Lowell's Observatory in Arizona, finally spotted something, a faint dot of light moving against the background stars. It was small, it was distant, it was roughly where Lowell had predicted Planet X might be. They named it Pluto, and for 76 years it sat at the end of the solar system as the 9th planet, a cold little world orbiting at about 39.5 astronomical units from the Sun. And for a while, that seemed like the end of the story. We had found Planet X, the solar system was complete again, textbooks were updated, Neptune was no longer the edge, Pluto was. But Pluto was strange. It was smaller than the Moon. Its orbit was tilted and elongated in ways that didn't match the neat circular paths of the other planets. It didn't clear its orbital neighborhood the way the big planets did. And as telescopes improved and surveys pushed deeper into the outer solar system, astronomers started finding other objects out there, not planets, not quite. Small icy bodies orbiting in the same general region as Pluto, following similar tilted paths made of the same frozen materials. One object, then another, then dozens, then hundreds. By the early 1990s, it became clear that Pluto wasn't alone. It wasn't even unusual. It was just the first large member of an entire population of icy bodies that had been sitting out there in the dark, unnoticed, for the entire history of astronomy. The region was named the Kuiper Belt, after Gerard Kuiper, a Dutch-American astronomer who had speculated in 1951 that a disk of icy debris might exist beyond Neptune. Kuiper wasn't the first to suggest it. Kenneth Edgeworth had proposed something similar a few years earlier, and the idea had roots going back even further. But Kuiper's name stuck, and by the mid-1990s, the Kuiper Belt was no longer a hypothesis. It was a confirmed structure, a vast reservoir of frozen objects encircling the outer solar system like a cosmic junkyard. Here's the scale, because the scale is where this stops being a footnote in astronomy and starts being something that changes the shape of the solar system in your head. The Kuiper Belt begins just beyond Neptune at roughly 39.5 astronomical units from the Sun. It extends outward to about 55 astronomical units in its main body, with outlying regions stretching even farther. That's a span of at least 15 to 20 astronomical units, depending on where you draw the boundaries. In more familiar terms, the Kuiper Belt is roughly 4.5 billion miles wide. 4.5 billion miles. Let that sit for a second. The distance from the Sun to Neptune is about 2.8 billion miles. The distance from the Sun to Earth is 93 million miles. The entire inner solar system, the region containing Mercury, Venus, Earth, and Mars, fits inside a sphere with a radius of about 140 million miles. The Kuiper Belt is wider than the entire inner solar system by a factor of more than 30. It is not a ring. It is not a thin ribbon of debris scattered along a single orbital path. It is a massive three-dimensional donut, a torus of frozen material encircling the Sun at a distance where sunlight is so faint that high noon on the surface of any object out there would look like deep twilight on Earth. And it is packed, not densely, not in the way a city is packed, or even the way the asteroid belt is packed. Space is still mostly empty, but astronomers estimate that there are hundreds of thousands of objects in the Kuiper Belt larger than 100 kilometers across, millions more smaller than that. Some are the size of mountains, some are the size of continents. A few are large enough to be called dwarf planets, small worlds in their own right, with enough mass to pull themselves into roughly spherical shapes. So far, we have catalogued about 2,000 Kuiper Belt objects. That's it. 2,000 out of hundreds of thousands, maybe millions. We are looking at a population that is almost entirely unknown. Most of the Kuiper Belt has never been photographed. Most of its inhabitants have never been named. They orbit in silence, too faint to see with anything but the largest telescopes, too far away for most spacecraft to ever visit, and every single one of them is a time capsule. The objects in the Kuiper Belt are leftovers, not leftovers in the sense of scraps or garbage, leftovers in the sense that they are pieces of the original material that formed the solar system 6 billion years ago, and they have been sitting out there, largely unchanged, ever since. They are made of the same ices and rock that clumped together to build the planets. Water ice, methane ice, ammonia, nitrogen, frozen volatiles that would have evaporated away if they had formed closer to the Sun. But at 40 or 50 astronomical units, the temperature is so low that these materials stay solid for billions of years. When the solar system was young, this region was full of material, a thick disk of gas and dust and ice surrounding the newborn sun, stretching outward for tens of billions of miles. The inner part of that disk condensed into rocky planets. The middle part built the gas giants. The outer part, the cold, distant edge where sunlight barely reached, stayed frozen. And as the planets grew, their gravity stirred the surrounding material. Jupiter and Saturn, the two largest planets, acted like cosmic bulldozers, scattering objects inward and outward, clearing out the space between them. Some of that scattered material fell into the sun. Some was flung out of the solar system entirely. And some of it ended up in the Kuiper Belt, where it has remained ever since, orbiting quietly, undisturbed by planetary migration or collisions or anything else that might have destroyed it or changed its composition. This is why the Kuiper Belt matters. It's not just a collection of icy rocks. It's a record, a fossil bed. The objects out there contain information about the early solar system that exists nowhere else. They tell us what the solar system looked like before the planets finished forming. They tell us what kinds of materials were available in the outer regions. They tell us how things moved and collided and clumped together in the chaos of the first few 100 million years. And we are only just starting to read that record. The story of the Kuiper Belt is also the story of why it took so long to find. Neptune was discovered in 1846, Pluto in 1930, but the first confirmed Kuiper Belt object other than Pluto wasn't spotted until 1992. That's 146 years after Neptune, 62 years after Pluto. Why the delay, distance, faintness, and the fact that nobody was looking in the right way? Kuiper Belt objects are small and dark. Most of them reflect less than 10% of the sunlight that hits them. At 40 astronomical units, even a relatively large object, something a few hundred kilometers across, looks like a dim speck of light barely distinguishable from a distant star. To find one, you need a powerful telescope, a sensitive camera, and a lot of patience. You take an image of a patch of sky. You wait a few hours or a few nights. You take another image of the same patch. Then you compare the two images, looking for anything that moved. Most things in the sky don't move, at least not noticeably over the span of a few hours. Stars stay put, galaxies stay put, but objects in the solar system move, and the closer they are, the faster they appear to shift against the background. Kuiper Belt objects move slowly because they're so far away, but they do move, and that motion is what gives them away. In 1992, astronomers David Jewett and Jane Liu, working at the Mauna Kea Observatory in Hawaii, finally found one. They had been searching for 5 years, scanning the sky methodically, looking for faint moving objects beyond Neptune. They found it on the night of August 30, 1992, a tiny dot of light drifting slowly across the star field. They designated it 1992 QB1, and its discovery confirmed what Kuiper and Edgeworth had speculated decades earlier. There was a population of objects out there, a belt, a structure. Within a few years, dozens more were found, then hundreds. The floodgates had opened. By the early 2000s, astronomers realized they were looking at one of the major structural components of the solar system, a region that had been invisible for the entire history of astronomy, simply because nobody had the tools to see it. And the more they looked, the stranger it got. The Kuiper Belt is not uniform. It has structure. There are different populations of objects with different orbital characteristics, and those differences tell a story about how the outer solar system evolved. Some objects orbit in nearly circular paths in the main belt between 42 and 48 astronomical units. These are called classical Kuiper Belt objects, and they're thought to be the least disturbed, the ones that have stayed in roughly the same place since the solar system formed. Others have orbits that are locked in gravitational resonance with Neptune. Pluto is one of these. For every 3 times Neptune orbits the Sun, Pluto orbits twice. That 3-to-2 resonance keeps Pluto's orbit stable even though it crosses Neptune's path. There are thousands of objects in similar resonances, and astronomers call them Plutinos. The resonances act like safe harbors, protecting these objects from being flung out of the solar system by Neptune's gravity. And then there are the scattered disk objects, bodies with highly elongated orbits that swing far beyond the main Kuiper Belt, out to 100 or 200 astronomical units or more, before swinging back in toward Neptune. These are thought to be objects that had close encounters with Neptune in the distant past and were scattered outward into these extreme orbits. Some of them may eventually escape the solar system entirely. Others may fall back inward and become comets. The Kuiper Belt, in other words, is not a static graveyard. It's dynamic. Objects are still colliding. Orbits are still shifting. The region is slowly grinding itself down, breaking larger bodies into smaller ones, generating dust that gets blown outward by the solar wind. Over billions of years, the Kuiper Belt has been losing mass, eroding away like a sandstone cliff battered by wind. And that erosion points to one of the biggest mysteries about the Kuiper Belt. There's not enough stuff in it. Current estimates put the total mass of the Kuiper Belt at somewhere between 0.2 and 0.1 Earth masses. That's a rounding error compared to the mass of the planets. It's not even close to the amount of material that should have been there when the solar system formed. Computer models of planetary formation suggest that the outer solar system should have started with a much larger reservoir of material, tens of Earth masses or more, enough to build several more Neptune-sized planets if things had gone differently. But that material is gone, most of it. 99% of it, maybe more. Something stripped the Kuiper Belt down to a thin shell of what it used to be, and the leading explanation is planetary migration. Jupiter, Saturn, Uranus, and Neptune didn't form where they are now. They formed closer to the Sun, in a more tightly packed configuration, and over the first few 100 million years of the solar system's history, they migrated outward, pushed by gravitational interactions with the disk of material around them. As Neptune moved outward, it plowed through the primordial Kuiper Belt like a wrecking ball, scattering most of the material inward toward the Sun or outward into interstellar space. What we see today is the survivors, the objects that managed to avoid being flung away, either because they were in stable resonances or because they were far enough out that Neptune's influence was weaker. This story, called the Nice model after the French city where it was developed, has become the leading explanation for the structure of the outer solar system. It explains why the Kuiper Belt is so depleted. It explains the resonances. It explains why Uranus and Neptune are where they are. And it explains one other thing that puzzled astronomers for decades. It explains where comets come from. Short-period comets, the ones that swing through the inner solar system every few decades or centuries, originate in the Kuiper Belt. Every now and then, a collision or a gravitational nudge sends one of these icy bodies spiraling inward toward the sun. As it approaches, the ice begins to vaporize, creating the glowing tail that makes comets so spectacular. Most of the famous comets, Halley's Comet, Comet Hale-Bopp, came from the Kuiper Belt. They are pieces of the outer solar system that wandered into our neighborhood, giving us a close-up look at material that normally stays frozen at 40 or 50 astronomical units. And now, finally, after decades of looking at the Kuiper Belt from a distance, humanity has sent a spacecraft out there. New Horizons, launched in 2006, became the first probe to visit the Kuiper Belt when it flew past Pluto in July 2015. The images it sent back were nothing like what anyone expected. Instead of a dead, cratered ice ball, Pluto turned out to be geologically active, with smooth plains of frozen nitrogen, towering mountains of water ice, and a thin atmosphere that freezes and falls to the surface as snow when Pluto moves farther from the Sun in its elliptical orbit. 4 years later, on New Year's Day 2019, New Horizons flew past a second Kuiper Belt object, a small body originally designated 2014 MU69 and later named Arrokoth. It was the most distant object ever visited by a spacecraft, sitting more than 4 billion miles from Earth, and it looked like nothing anyone had seen before. But that's the next part of the story. For now, the point is this: the Kuiper Belt is real. It is enormous. It is full of objects we have barely begun to catalogue, let alone understand, and it is the true edge of the planetary solar system, the place where the sun's influence starts to fade and the long fall into interstellar space begins. Neptune isn't the edge, it's the gate, and beyond that gate lies a frozen wilderness that has been waiting, untouched, since the day the solar system was born. So Pluto was supposed to be dead. That was the assumption baked into every textbook, every mission proposal, every quiet conversation astronomers had about what humanity might find if we ever managed to send a spacecraft that far out. Pluto was small, roughly 2/3 the diameter of our moon. It was cold, sitting 39.5 astronomical units from the Sun, where temperatures hover around -230 degrees Celsius. And it was old, 4.5 billion years old, the same age as everything else in the solar system. Small cold worlds do not stay geologically active. They freeze solid early in their history and stay that way. The heat generated by their formation bleeds away into space. Their interiors solidify. Their surfaces lock into place, scarred by billions of years of impacts, and nothing moves again. That is the rule, and Pluto by every measure should have followed it. The prediction was straightforward. When New Horizons finally arrived at Pluto, after a 9.5-year journey across the solar system, it would photograph a lifeless ball of ancient ice, cratered beyond recognition, inert, silent, and thoroughly uninteresting except for the fact that it was there and we had never seen it up close. The images would be scientifically valuable in the way that all data is valuable, but nobody expected to be surprised. Nobody expected to be wrong. Then, on July 14th, 2015, New Horizons flew past Pluto at a distance of about 7,800 miles. moving at more than 30,000 miles per hour, and the pictures started coming back, and every single assumption fell apart. Pluto was not dead. It was not a uniform cratered wasteland. It was not frozen in time. It was active, diverse, and geologically young in places, so young that some regions of its surface appeared to have formed within the last few million years. In geological terms, that is yesterday. On a world that should have been a fossil, New Horizons found a beating heart, literally. One of the first features to jump out of the images was a massive bright region shaped almost exactly like a heart, sprawling across Pluto's equator. The western lobe of that heart, a smooth plain roughly the size of Texas, was named Sputnik Planitia, and it became the single most surprising discovery of the entire mission. Sputnik Planitia is an impact basin. At some point in Pluto's history, something large slammed into the surface and carved out a depression more than 1,000 kilometers across. Over time, that basin filled with ice, not water ice, though there is plenty of that on Pluto. Nitrogen ice. Nitrogen, the same gas that makes up most of Earth's atmosphere, freezes solid at the temperatures found on Pluto's surface. And once it is frozen, it behaves in strange ways. Nitrogen ice is soft, it flows. It is more like a very thick liquid than a solid rock, and under the right conditions, it can move across a planetary surface the way glaciers move on Earth, except nitrogen glaciers move faster. Some estimates suggest that the ice in Sputnik Planitia shifts by roughly a kilometer over the course of a single Pluto year, which lasts 248 Earth years. That is not fast by human standards, but it is absolutely screaming by geological ones. And the ice is not just flowing, it is convecting. The surface of Sputnik Planitia is divided into polygonal cells, each one tens of kilometers across, with bright centers and darker edges. Those cells are the visible signature of convection, the same process that drives weather on Earth and makes soup boil on a stove. Warmer nitrogen ice, heated slightly by Pluto's interior, rises toward the surface in the center of each cell. As it reaches the top, it cools, spreads outward, and sinks back down along the edges. The cycle repeats endlessly, turning over the entire surface of the plane on timescales of hundreds of thousands of years. That is why Sputnik Planitia has almost no craters. Craters require a surface that stays put long enough for impacts to accumulate. A surface that is constantly recycling itself erases its own impact record. The ice churns, the craters vanish, and what you are left with is a smooth, bright plain that looks brand new because, in a very real sense, it is. The existence of convection on Pluto is not supposed to be possible. Convection requires heat. On Earth, that heat comes from the sun and from the planet's molten interior. Pluto has neither. The sun is a dim point of light at 40 astronomical units, providing almost no warmth. Pluto's interior should have frozen solid billions of years ago, killed by its own small size. Small bodies lose heat faster than large ones because they have more surface area relative to their volume. A marble cools faster than a bowling ball. A moon cools faster than a planet. Pluto, at roughly 1/400th the mass of Earth, should have cooled into a solid block of rock and ice within the first few 100 million years of its existence. Instead, something is keeping it warm, not hot, not molten, but warm enough that nitrogen ice a kilometer deep can flow and churn and reshape the surface in real time. One possibility is radiogenic heating. Pluto's rocky core contains trace amounts of radioactive elements, uranium, thorium, potassium, left over from the solar system's formation. These elements decay over billions of years, releasing heat as they break down into lighter elements. On Earth, Radiogenic decay is a significant heat source, contributing to the warmth that keeps the mantle molten and drives plate tectonics. On a body as small as Pluto, the effect should be negligible. But if the concentration of radioactive elements in Pluto's core is higher than expected, the decay could generate enough heat to warm the base of the ice shell and drive convection in the overlying nitrogen. Another possibility, one that has gained traction since New Horizons, is that Pluto has a subsurface ocean. Not on the surface where it would freeze instantly, but buried deep beneath the ice shell, a layer of liquid water sitting between the rocky core and the frozen crust. Subsurface oceans are not as exotic as they sound. We are almost certain that Jupiter's moon Europa has one, along with Saturn's moons Enceladus and possibly Titan. Even Pluto's largest moon, Charon, might have had a subsurface ocean early in its history before it froze. The evidence for an ocean on Pluto comes from several lines of reasoning. First, the surface shows large fractures and faults, the kind you would expect if the interior had expanded or contracted at some point, flexing the crust. Second, Sputnik Planitia itself sits almost exactly on Pluto's equator, directly opposite the largest moon Charon. That alignment is unlikely to be a coincidence. The basin is heavy, filled with dense nitrogen ice, and over millions of years, the weight of that ice could have caused Pluto to reorient itself, rolling until the basin settled at the point where it balances the tidal forces from Charon. That kind of reorientation is easier if there is a liquid layer inside Pluto that can slosh around and decouple the crust from the core. Third, the existence of ongoing geological activity on a world this small and this cold is hard to explain without an internal heat source more powerful than radiogenic decay alone. A subsurface ocean, kept liquid by tidal heating and insulated by kilometers of ice, could provide that heat. It could drive the convection in Sputnik Planitia, power the fractures cutting across Pluto's surface, and explain why some regions look geologically young. None of this is confirmed. New Horizons flew past Pluto in a matter of hours and did not carry instruments designed to detect subsurface oceans. What we have are clues, indirect evidence, and models that suggest an ocean is not only possible but likely. If it exists, it is one of the strangest results to come out of the mission. A liquid water ocean on a dwarf planet at the edge of the solar system, sitting beneath a crust of water ice and a surface coated in frozen nitrogen, invisible to every telescope humanity has ever built, detectable only by the subtle flexing of the ground above it. And it is not the only strange thing New Horizons found. Pluto's surface is not uniform. It is a patchwork of different terrains, each one telling a different story about what has happened there. To the east of Sputnik Planitia, the landscape is ancient and heavily cratered, a record of billions of years of impacts. To the west, there are mountains. Not small hills, mountains, towering peaks of water ice rising several kilometers above the surrounding plains. Water ice at Pluto's temperatures is as hard as granite, and these mountains appear to be floating in the surrounding nitrogen ice like icebergs in a sea. Water ice is less dense than nitrogen ice, so it floats, and as the nitrogen convects and flows, the mountains drift along with it, carried by currents too slow to see but powerful enough to reshape the geography over geological time. There are also regions of chaotic terrain, jumbled landscapes where the surface looks like it has been broken apart and refrozen, possibly by the expansion of a subsurface ocean or by the collapse of ice layers as volatile materials sublimated away. There are wind streaks, dark trails of material blown across the surface by Pluto's thin atmosphere. There are dunes, rows of parallel ridges that appear to be made of methane ice grains carried by winds and deposited in patterns that look eerily similar to sand dunes on Earth or Mars. And there is Right Mons, a massive mountain roughly 4 kilometers high with a deep depression at its summit. Some researchers have suggested it might be a cryovolcano, a volcano that erupts not molten rock, but a slurry of water, ammonia and methane. If that is true, it would mean that Pluto has been volcanically active in the geologically recent past, venting material from its interior onto the surface the way Earth's volcanoes vent lava. The existence of cryovolcanism on Pluto is still debated. New Horizons did not catch a volcano in the act of erupting, and the features that look like volcanic constructs could have other explanations, but the possibility alone is remarkable. Volcanoes require internal heat, pressure, and a pathway for material to reach the surface. On a world as small and as cold as Pluto, the fact that any of those conditions might be met is a testament to how much we underestimated what the outer solar system is capable of. Then there is the atmosphere. Pluto has one, a thin envelope of nitrogen gas with traces of methane and carbon monoxide, barely thicker than the vacuum of space, but still substantial enough to have weather. The atmospheric pressure at Pluto's surface is about 100,000th of Earth's, but that is enough for the gas to interact with the surface, to sublime and condense, to form hazes and clouds, and to transport material from one region to another. The atmosphere is not stable. It changes with Pluto's orbit. Pluto's orbit is highly elliptical, swinging from 30 astronomical units at its closest approach to the Sun to nearly 50 astronomical units at its farthest. When Pluto is near perihelion, the closest point in its orbit, the surface warms slightly and nitrogen ice sublimates, thickening the atmosphere. When Pluto moves toward aphelion, the farthest point, the atmosphere cools and collapses, freezing out onto the surface as snow. This cycle takes 248 years, and we have only observed a tiny fraction of it. New Horizons arrived near perihelion, so the atmosphere was relatively thick by Pluto's standards. Images taken during the flyby show layers of haze extending more than 100 kilometers above the surface, illuminated by the sun in a thin crescent of light. The haze is made of tiny particles, probably complex hydrocarbons, formed when ultraviolet light from the sun breaks apart methane molecules in the upper atmosphere. Those particles fall slowly through the thin air and eventually settle on the surface, where they may be responsible for some of the dark reddish material seen in certain regions. Pluto's atmosphere also appears to drive surface processes. The wind streaks visible in New Horizons images suggest that winds on Pluto, though weak by Earth standards, are strong enough to pick up small grains of ice and deposit them elsewhere. The dunes near Sputnik Planitia are further evidence of atmospheric transport, and some models suggest that the redistribution of volatile ices by wind and sublimation could be shaping Pluto's surface on timescales of thousands to millions of years. This is not a dead world. This is a world with weather, with seasons, with a surface that responds to its atmosphere and an atmosphere that responds to its surface. It is a climate system, primitive and alien, but recognizable in its basic structure. Nitrogen condenses in the cold regions and sublimates in the warmer ones. Methane cycles between ice and gas. Hydrocarbons form in the upper atmosphere and rain down onto the plains. The system is slow, operating on time scales that make Earth's glacial cycles look rapid, but it is active. It is happening right now. And all of this complexity exists on a world that is smaller than Russia, orbiting in near darkness at the edge of the planetary solar system. The reaction to New Horizons discoveries was immediate and widespread. Scientists who had spent their careers studying Pluto from a distance suddenly had to rewrite their models. The public, which had largely written off Pluto as a distant footnote after its reclassification as a dwarf planet in 2006, rediscovered it as one of the most interesting objects in the solar system. The image of the heart became iconic, reproduced in news articles, science textbooks, and promotional material for the mission. Pluto stopped being the X-planet that got kicked out of the club and became the dwarf planet that refused to behave. Alan Stern, the principal investigator for New Horizons, described the findings as a complete surprise. Nobody expected this level of activity. Nobody predicted the diversity. The mission had been designed to answer basic questions about what Pluto looked like, what it was made of, and how it fit into the broader population of Kuiper Belt objects. Instead, it raised new questions, harder questions, about how small worlds generate and retain heat, how atmospheres behave at extreme distances from the Sun, and whether the conditions for geological activity might be far more common in the outer solar system than anyone had imagined. The debate over Pluto's planetary status, which had raged since 2006, took on a new dimension. The International Astronomical Union's definition of a planet requires that an object clear its orbital neighborhood, sweeping up or ejecting other debris. Pluto does not do that. It orbits in the Kuiper Belt, surrounded by thousands of other objects, and by that definition, it is not a planet. Many scientists and much of the public disagreed with the decision, arguing that the definition was arbitrary and ignored the intrinsic properties of the object itself. New Horizons did not settle that debate. If anything, it intensified it. Here was a world with mountains, glaciers, a subsurface ocean, an atmosphere, and active geology. It had everything that made the classical planets interesting. And yet, by the official definition, it was not a planet. The controversy remains unresolved, and it probably always will be. What New Horizons did settle was the question of whether small, icy worlds matter. They do. They are not simple, they are not uniform, and they are not dead. Pluto is proof that size alone does not determine whether a world is geologically active or scientifically interesting. The outer solar system, it turns out, is full of places that defy the rules we wrote based on the inner planets, and Pluto is just one of them. 9 years after launch, after a journey of more than 3 billion miles, New Horizons spent a few hours in Pluto's neighborhood, collected as much data as its instruments could hold, and kept going. It did not stop. It could not stop. Its trajectory carried it deeper into the Kuiper Belt, away from the Sun, toward another target, another frozen world waiting in the dark. That next target was smaller than Pluto, stranger than Pluto, and older in a way that made it one of the most scientifically valuable objects New Horizons would ever visit. Its name was Arrokoth, and it was about to teach us what the solar system looked like before any of the planets existed. So New Horizons was alone, 4 billion miles from Earth, moving at more than 30,000 miles per hour, barreling through a region of space so empty that the nearest star would take 70,000 years to reach at current speed. The Pluto flyby had been the mission's climax, the moment everyone had been waiting for, and it had delivered beyond anyone's expectations. But the spacecraft was still functional. Its instruments were intact. Its power supply, a small plutonium generator slowly decaying in the darkness, still had years of life left, and its trajectory was carrying it deeper into the Kuiper Belt, into a region no spacecraft had ever entered, toward objects no human eye had ever seen up close. The question was whether there was anything out there worth visiting. This was not a trivial problem. Spacecraft do not steer like cars. They cannot take sharp turns or reverse direction. Once New Horizons left Pluto, Its path was essentially fixed. The only way to visit another object was to find one that already happened to be sitting along the narrow corridor of space the spacecraft would pass through over the next few years. That corridor was tiny, a cone of possible trajectories stretching outward from Pluto's location, and the Kuiper Belt, while vast, is not densely populated. Most of its objects are separated by millions of miles. The odds of finding something close enough to reach with the fuel New Horizons had left were not good. The mission team started searching before New Horizons even reached Pluto. They used the Hubble Space Telescope, the most powerful tool available for spotting faint distant objects, and they pointed it at small patches of sky along New Horizons' projected path. They were looking for anything that moved, anything that reflected enough sunlight to register as more than background noise. The search took years. Hubble looked and found nothing. Then it looked again and again. The team expanded the search area, scanned adjacent regions, and kept looking. In June 2014, nearly a year before the Pluto flyby, Hubble finally spotted something, a faint dot of light, barely distinguishable from the stars behind it, moving slowly across the field of view. Follow-up observations confirmed it was a Kuiper Belt object, small and distant, sitting almost exactly where New Horizons would be able to reach it with a minor course correction. The team designated it 2014 MU69, a placeholder name pulled from the catalog system astronomers use to track newly discovered objects. Later, they gave it a nickname, Ultima Thule. Ultima Thule is a Latin phrase meaning the farthest north, a term that appears in ancient and medieval texts to describe the most distant land at the edge of the known world. It felt appropriate. This object was the farthest thing New Horizons could visit, sitting more than 1 billion miles beyond Pluto, and it represented the absolute limit of what the mission could reach before the spacecraft ran out of power and drifted into silence. The nickname stuck for years, but it carried baggage. Ultima Thule had been appropriated by various groups throughout history, including Nazi occultists who used it as a symbol of Aryan mythology. When the New Horizons team announced the nickname publicly, there was pushback. Some argued the name had uncomfortable associations and should be replaced. Others defended it, pointing out that the phrase predated its misuse by centuries and had legitimate historical and literary roots. The debate simmered for months. Eventually, the International Astronomical Union assigned the object an official name, Arrokoth, a word from the Powhatan language meaning sky. The Powhatan are indigenous people of the Chesapeake Bay region, and the name was chosen in collaboration with representatives from the Powhatan community. It was meant to honor the heritage of the land where New Horizons was built and launched, and it replaced the controversial nickname officially in late 2019. For the purposes of this story, the name matters less than what the object turned out to be. Arrokoth is small. Its longest axis measures about 36 kilometers, roughly the length of Manhattan from tip to tip. Its shortest dimension is closer to 10 kilometers. It is not a sphere. It is not even close to spherical. It looks, and this is the description that appeared in every news article after the flyby, like a snowman. 2 lobes, one slightly larger than the other, joined at a narrow neck. The larger lobe is flatter and more pancake-shaped. The smaller lobe is rounder, closer to an oblate sphere. Together they form a contact binary, 2 separate objects that formed independently and at some point in the distant past drifted close enough to touch and stick together. That shape is strange. Not because contact binaries are rare, they are not. Comets often turn out to be contact binaries when we get close-up images. Comet 67P, visited by the European Space Agency's Rosetta mission, has a similar double-lobed structure. But Arrokoth is not a comet. It has never been anywhere near the Sun. It has been sitting in the Kuiper Belt, more than 40 astronomical units from the Sun, for the entire 4.5 billion year history of the solar system. It has not been melted. It has not been reshaped by tidal forces. It has not been battered into its current form by violent collisions. The shape it has now is, as far as anyone can tell, the shape it has always had. New Horizons flew past Arrokoth on January 1st, 2019, at a distance of about 3,500 kilometers, moving at roughly 50,000 kilometers per hour relative to the object. The flyby lasted minutes. The spacecraft's cameras took hundreds of images as it approached, capturing the object from different angles, resolving details down to about 30 meters per pixel in the best shots. The data took months to transmit back to Earth. At that distance, radio signals traveling at the speed of light take more than 6 hours to cover the gap one way. Every image, every spectrograph reading, every measurement New Horizons made had to be sent bit by bit over a radio link so faint that NASA's Deep Space Network, the array of massive dish antennas used to communicate with distant spacecraft, had to strain to hear it. When the images arrived, they showed something nobody had predicted. Arrokoth was smooth, not perfectly smooth. There were subtle variations in its surface, slight changes in color and texture, small hills and shallow depressions, but there were almost no craters, no large impact scars, no signs of violent collisions. The surface was pristine, unmarred, as if the object had been sitting in a cosmic freezer since the day it formed, untouched by the chaos that shaped the rest of the solar system. That absence of craters is one of the most important details. Craters are the solar system's clock. Every solid surface in the solar system accumulates impact craters over time, as smaller objects collide with it at high speed. The Moon is covered in craters. Mars is covered in craters. Mercury, asteroids, the moons of Jupiter and Saturn, all of them bear the scars of billions of years of impacts. The older the surface, the more craters it has. A surface with no craters is either very young, meaning it has been resurfaced recently by geological activity, or it has been sitting in a region of space where collisions are extremely rare. Arrokoth is not geologically active. It is far too small to generate internal heat. Its surface temperature hovers around -230 degrees Celsius, cold enough that almost nothing can move or flow. There are no volcanoes, no plate tectonics, no convection. The lack of craters, therefore, does not mean the surface is young. It means Arrokoth has been sitting in an extraordinarily quiet neighborhood for 4.5 billion years, a region where the impact rate is so low that even over geological timescales, almost nothing has hit it hard enough to leave a mark. That tells us something profound about the Kuiper Belt. It is not a shooting gallery. It is not a chaotic debris field where objects are constantly smashing into each other at high speed. It is a sparse, stable region where most objects follow predictable orbits and close encounters are rare. The violence that characterized the early solar system, the period when planets were forming and scattering material inward and outward, mostly bypassed this part of space. The Kuiper Belt, or at least the region where Arrokoth orbits, has been calm for billions of years. The shape of Arrokoth tells the second part of the story. The two lobes did not collide violently, they merged gently. The evidence for this is written into the geometry of the contact point. If two objects slam into each other at high speed, they deform, they shatter, they produce debris. The resulting shape is chaotic, with sharp edges, fragmented surfaces, and clear signs of impact compression. Arrokoth shows none of that. The neck connecting the two lobes is smooth. There are no shattered fragments, no compression features, no signs of a high-energy impact. Computer simulations of the merger suggest the two lobes came together at a relative speed of less than 3 meters per second. Some models put the speed even lower, closer to 1 meter per second. That is walking speed. Imagine two city-sized chunks of ice and rock drifting through space at the speed of a slow stroll, brushing against each other and sticking. That is what happened to Arrokoth. The collision was so gentle that it did not even crack the surfaces of the two lobes. They simply touched and stayed together, held by gravity and the weak forces that cause icy materials to bond when they are in contact. This has enormous implications for how planets form. For decades, the standard model of planet formation assumed that small bodies in the early solar system grew by violent collisions. Dust grains stuck together to form pebbles. Pebbles collided to form rocks. Rocks smashed into each other to form boulders. Boulders collided at high speed, sometimes shattering, sometimes sticking, gradually building up larger and larger objects through a process called accretion. The process was chaotic, inefficient and slow, and it required objects to collide at speeds high enough to overcome their mutual gravitational attraction, but low enough that they did not destroy each other. Arrokoth suggests a different process. Its two lobes are roughly the same size, they are made of the same materials, they have similar shapes, and they merged at a speed so low that it is hard to explain how they ever got close enough to collide in the first place, unless they formed very near each other, in a region of the protoplanetary disk where the local density of material was high and the relative velocities between objects were extremely low. One model that fits the data is called gravitational collapse. In this scenario, a dense clump of material in the protoplanetary disk, perhaps a region where particles had concentrated due to turbulence or pressure gradients, began to collapse under its own gravity. As it collapsed, it fragmented into smaller clumps, each one pulling itself together into a roughly spherical shape. Those clumps, now small planetesimals, continued to orbit in the same general region, moving at nearly the same speed because they had all formed from the same collapsing cloud. Over time, their orbits brought them close enough to touch, and when they touched, they stuck. This is a much gentler process than the traditional collision model. It does not require high-speed impacts, it does not produce a lot of debris, and it predicts that many small bodies in the Kuiper Belt should be contact binaries, formed from the merger of objects that were born as neighbors in the same collapsing cloud. Arrokoth is the first object we have seen up close that fits this model perfectly. Its shape, its lack of craters, the smoothness of the merger, all of it points to a formation process that was slow, cold, and extraordinarily gentle. It is a snapshot of what planetesimal formation looked like in the outer solar system 4.5 billion years ago, frozen in place and preserved in the deep cold of the Kuiper Belt. The surface of Arrokoth provides additional clues. Spectrographic measurements taken by New Horizons detected methanol, water ice, and organic molecules on the surface. The organic molecules are complex carbon-based compounds, likely formed by the irradiation of simpler ices by cosmic rays and ultraviolet light from distant stars over billions of years. This kind of processing happens slowly, it requires time, and it produces a distinctive reddish color, the result of organic compounds called tholins that coat the surface like rust on metal. Arrokoth is red, very red. It is the reddest object New Horizons has ever visited, redder even than Pluto. The red color is not paint, it is not a mineral. It is the accumulated product of 4.5 billion years of radiation, slowly breaking apart methanol and other simple molecules on the surface and reassembling them into more complex organic compounds. Those compounds darken over time, shifting from white or grey to orange to deep red. The intensity of the red color on Arrokoth suggests that its surface has been exposed to space for an extremely long time without being disturbed by impacts or covered by fresh ice. That matches the cratering record, or rather the lack of one. If Arrokoth's surface had been churned by impacts or resurfaced by volcanic activity or covered by fresh material from cometary outgassing, the red color would have been erased. The fact that the color is so uniform and so intense means the surface has been sitting undisturbed for billions of years, slowly darkening as cosmic rays and starlight cook its ices into tholins. This makes Arrokoth a time capsule in the most literal sense. It is a sample of the early solar system that has not been altered by heat, pressure, collisions, or chemical reactions. The materials on its surface are the same materials that were present in the protoplanetary disk 4.5 billion years ago, preserved in their original state by the extreme cold and isolation of the Kuiper Belt. If you wanted to know what the solar system looked like before the planets formed, before the sun ignited, before anything resembling a habitable environment existed, you would study Arrokoth. The scientific return from the Arrokoth flyby has been enormous. The mission provided the first clear evidence that planetesimals in the outer solar system formed by gentle gravitational collapse rather than violent collisions. It showed that the Kuiper Belt is a low-collision environment where objects can survive for billions of years without being destroyed or significantly altered. It revealed that organic chemistry has been happening on Kuiper Belt objects since the solar system formed, producing complex molecules that may be similar to the building blocks of life. And it demonstrated that small, primitive objects in the outer solar system can retain detailed information about their formation conditions, information that has been erased everywhere else by planetary migration, impacts, and thermal processing. Kerry Liss, a planetary scientist working on the New Horizons mission, described Arrokoth as a cold, classical Kuiper Belt object, meaning it belongs to a population of objects that have remained in stable orbits since the solar system formed. Their orbits have not been perturbed by Neptune. They have not been scattered inward or outward by gravitational interactions with the giant planets. They have been sitting in the same region of space, following the same paths, for 4.5 billion years. Arrokoth's orbit, Liss said, has been pretty much the same for the entire history of the solar system. That stability is rare. Most objects in the solar system have been moved around. The planets migrated. The asteroid belt was stirred by Jupiter. Comets were scattered from the Kuiper Belt into the inner solar system. Even the orbits of the giant planets themselves shifted over the first few 100 million years of the solar system's history. Very few objects have stayed put. Arrokoth is one of them. Its orbit is a relic, a piece of the original architecture of the solar system that has not been remodeled or torn down. And because it has stayed in the same place, it has also stayed the same physically. It has not been melted by passing close to the sun. It has not been broken apart by collisions. It has not been reshaped by tidal forces. It is, in almost every measurable way, the same object it was when it formed. The term time capsule gets thrown around a lot in planetary science, but it is rarely as accurate as it is for Arrokoth. This is not an object that has been modified and then preserved. It is an object that never needed to be preserved because nothing ever happened to it. It formed, it cooled, and it drifted for 4.5 billion years. That is the story. New Horizons is still out there. It is still moving. It is currently more than 50 astronomical units from the Sun, deeper into the Kuiper Belt than any other functioning spacecraft. Its plutonium power source is decaying, and eventually, probably sometime in the 2030s, It will no longer generate enough electricity to keep the instruments running or the radio transmitter powered. When that happens, the spacecraft will go silent. It will keep moving, coasting outward at more than 30,000 miles per hour, but it will no longer be able to send data back to Earth. It will become another object in the Kuiper Belt, another piece of frozen hardware drifting through the dark. But the data it has already sent back will last. The images of Pluto, the close-ups of Arrokoth, the measurements of the Kuiper Belt's environment, its dust, its magnetic fields, its radiation, all of that is stored, catalogued, and being analyzed by researchers who will spend years, maybe decades, extracting every piece of information they can from the dataset. The mission is over in the sense that no new targets are within reach, but the science is just beginning. And what that science is revealing is that the Kuiper Belt is not a graveyard. It is an archive, a library, a place where the solar system's oldest stories are still written in stone and ice, waiting to be read by anyone who can make the journey and look closely enough. Arrokoth is one page of that story, a page that has not been torn, burned, or rewritten. A page that still says exactly what it said 4.5 billion years ago, in a language we are only now beginning to understand. But Arrokoth is just one object. There are hundreds of thousands of others out there, most of them unseen, unmapped, and unnamed. And the more we look, the more we realize that the Kuiper Belt is not a simple disk of debris. It is a structure. It has boundaries. It has populations with different orbital characteristics, different compositions, different histories. Some of those populations fit neatly into the models we have built. Others do not. And the edges of the Kuiper Belt, the places where it fades into the darkness beyond, are still poorly understood. We do not know where it ends. We do not know what lies beyond it. And we are only beginning to realize how much we have missed. So here is what we thought we knew. The Kuiper Belt begins at roughly 30 astronomical units from the Sun, just beyond Neptune's orbit. It extends outward in a broad donut-shaped disk, thinning as it goes, until somewhere around 50 astronomical units, maybe 55 on the generous side, the population of icy objects drops off sharply. Beyond that outer edge, you hit the scattered disk, a separate population of bodies on wild, elongated orbits that swing far out into space before looping back toward the inner solar system. The scattered disk blends into something even more diffuse, a region where objects are so sparse and so distant that calling it a structure at all feels like a stretch. And beyond that, nothing. The long, empty fall toward interstellar space. That was the model. Clean boundaries, well-defined populations, a solar system that made sense on paper. The Kuiper Belt was big, yes, spanning billions of miles and containing hundreds of thousands of objects larger than 100 kilometers across. But it was finite. It had edges. You could point to a number, 50 astronomical units, and say with reasonable confidence that past that distance, the main belt was done. There might be stragglers, outliers, the occasional detached object wandering through on a lonely orbit, but the bulk of the population, the dense core of icy debris left over from the solar system's formation, stopped around 50 astronomical units. The textbooks said so. The surveys said so. The computer models, built on decades of observations and fine-tuned to match the distribution of known objects, said so. And then in late 2024, a dust counter on a spacecraft in the outer solar system started reporting numbers that did not fit. The spacecraft in question was New Horizons, the same probe that had flown past Pluto in 2015 and Arrokoth in 2019. After the Arrokoth flyby, the mission entered what NASA calls its extended mission phase, A polite way of saying the spacecraft is still working but has run out of major targets to visit. New Horizons is still moving, still functional, still collecting data as it drifts deeper into the Kuiper Belt. Its instruments are aging, its power supply is slowly decaying. But it is still listening, still watching, still measuring the environment around it as it travels farther from the Sun than any other active spacecraft in history. One of those instruments is called the Student Dust Counter, a detector mounted on the spacecraft's exterior designed to measure impacts from tiny grains of dust floating through space. Dust in the solar system comes from a variety of sources. Comets shed it as their ices sublimate. Asteroids produce it when they collide. Kuiper Belt objects generate it through micrometeorite impacts that chip away at their surfaces over billions of years. The dust drifts through space, propelled by radiation pressure from the Sun, gravitational interactions with the planets, and the slow grinding collisions that have been happening since the solar system formed. It is everywhere, a faint haze of microscopic particles that fills the space between worlds. The Student Dust Counter has been operating since New Horizons launched in 2006, recording every dust grain that hits its detector as the spacecraft traveled from Earth to Jupiter to Pluto and beyond. The data it collected over the years painted a consistent picture. Dust density in the inner solar system is relatively high, peaking near the asteroid belt where collisions are more frequent. As you move outward, the density drops. By the time you reach the orbit of Neptune, dust impacts are less frequent. The environment is cleaner, quieter. Models predicted that beyond 50 astronomical units, the dust density would drop even further, fading into near nothingness as the Kuiper Belt thinned out and the spacecraft entered the relatively empty space beyond. That is not what happened. Starting around 52 astronomical units, the dust counter began detecting impacts at a rate higher than it had measured since passing Jupiter, not slightly higher, significantly higher. The increase was steady, persistent, and completely unexpected. As New Horizons pushed past 55 astronomical units, then 60, the impact rate kept climbing. At 60 astronomical units, more than 5.5 billion miles from the Sun, the spacecraft was recording more dust impacts per day than it had seen at 40 astronomical units, deep inside the heart of the Kuiper Belt. The initial reaction among the mission team was skepticism. Dust counters can be fooled. Cosmic rays can trigger false detections. Instrument degradation over 18 years of spaceflight can introduce noise into the data. The team ran diagnostics, checked calibration records, compared the dust counter's readings with data from other instruments. Everything checked out. The detections were real. The dust was there. So the question became, where is it coming from? Dust does not appear out of nowhere. It has to be produced by something. In the inner solar system, that something is obvious. Comets, asteroids, collisions, all of it happening in relatively crowded regions where objects are numerous and close together. In the outer Kuiper Belt, the environment is supposed to be sparse. Objects are separated by millions of miles. Collision rates are low. The population density drops off beyond 50 astronomical units, which is why models predicted a corresponding drop in dust. If there are fewer objects, there are fewer collisions. If there are fewer collisions, there is less dust. But New Horizons was detecting more dust, not less. And the only way to explain that is to accept that the models were wrong about how sparse the outer Kuiper Belt actually is. Either there are more objects out there than anyone realized, or the dust is being generated by a process that the models did not account for, or the Kuiper Belt does not end where we thought it did. Maybe all three. The traditional picture of the Kuiper Belt divides it into three main populations. The classical Kuiper Belt objects, sitting in relatively stable orbits between about 42 and 48 astronomical units, are the least disturbed, the ones that have stayed in roughly the same place since the solar system formed. Then there are the resonant objects, like Pluto, locked into orbital resonances with Neptune that keep them from being scattered. And finally, the scattered disk, a population of objects on highly elliptical orbits that swing far beyond the main belt before looping back in toward Neptune. The scattered disk is thought to be the source of short-period comets, bodies that were once in the Kuiper Belt but got kicked onto unstable orbits by gravitational interactions with the giant planets. This three-part model has worked well for decades. It explains the orbital distribution of known Kuiper Belt objects. It accounts for the differences in composition and size between different populations. It matches the predictions of computer simulations of how the outer solar system evolved after the planets formed, and it includes a feature that astronomers have been puzzling over since the late 1990s, something called the Kuiper Cliff. The Kuiper Cliff is not a physical structure. It is a sharp drop in the number of observed objects beyond about 50 astronomical units. Surveys using the most powerful telescopes on Earth have catalogued thousands of Kuiper Belt objects, and the vast majority of them orbit between 30 and 50 astronomical units. Beyond that distance, the number of detections falls off dramatically, not gradually, sharply. It is as if someone drew a line in space and said, "This far and no farther." Several explanations have been proposed for the Kuiper Cliff. One is that the outer Kuiper Belt was cleared out by a passing star early in the solar system's history, a close encounter that stripped away the outermost material and left a sharp edge behind. Another is that Neptune's migration through the early Kuiper Belt scattered most of the objects beyond 50 astronomical units outward into the scattered disk, or inward toward the Sun, leaving very little behind in the outer classical belt. A third explanation is that the cliff is an observational artifact, a product of the fact that objects beyond 50 astronomical units are so faint and so far away that our surveys simply have not found them yet. The dust counter data from New Horizons suggests the third explanation might be correct. If there is a significant population of small objects, things too small to be detected by ground-based telescopes, but numerous enough to produce dust through collisions, then the Kuiper Belt could extend much farther than the distribution of large objects suggests. The Kuiper Cliff might not be a real boundary. It might just be the limit of what we can see from Earth. This is not a new idea. Astronomers have speculated for years that the Kuiper Belt might be more extended than observations suggest. But speculation is cheap. Data is not. And the student dust counter is providing the first direct measurement of the environment beyond the classical Kuiper Belt, the first real evidence that something is out there generating dust at distances where the models said there should be almost nothing. The implications are unsettling. If the Kuiper Belt extends significantly beyond 50 astronomical units, then the outer solar system is larger, more massive, and more complex than current models account for. The boundary between the Kuiper Belt and the scattered disk becomes blurrier. The transition from the planetary solar system to the realm of distant icy bodies becomes more gradual, and the question of where the solar system actually ends becomes harder to answer. Distance in the outer solar system stops feeling intuitive very quickly. 50 astronomical units is 4.6 billion miles. 60 astronomical units is 5.6 billion miles. The difference, a billion miles, is more than 10 times the distance from the Earth to the Sun. At those scales, the idea of a sharp boundary feels arbitrary. Space is not a map with borders, it is a continuum. Objects do not know they are supposed to stop existing past a certain distance just because a model says so. The dust New Horizons is detecting could be coming from small Kuiper Belt objects that have been there all along, grinding away at each other over billions of years, too faint to show up in surveys but numerous enough to produce a steady stream of dust. It could be coming from a population of objects in the scattered disk that spend most of their time at extreme distances but occasionally pass through the region New Horizons is traversing. It could be coming from a previously unknown population sitting in a part of the Kuiper Belt that has never been systematically surveyed because it is too far away and too faint to study with current telescopes. Or it could be evidence of something stranger. There is a fourth population of Kuiper Belt objects that does not fit neatly into the classical resonant or scattered disk categories. These are called detached objects, and they are some of the most peculiar things in the solar system. Detached objects have orbits that never bring them closer to the Sun than about 40 astronomical units, and some of them swing out to distances of several hundred astronomical units or more. They are called detached because their orbits are too far out to be explained by gravitational interactions with Neptune. Neptune's influence extends to about 40 astronomical units. Beyond that, its gravity weakens rapidly. An object with a perihelion, its closest approach to the Sun, at 50 or 60 astronomical units is too far away for Neptune to have scattered it there. So how did they get there? The leading explanation is that they were scattered by something else, another planet, a massive object that used to be in the outer solar system but is no longer there, either because it was ejected by gravitational interactions with the other giant planets, or because it is still there, orbiting far beyond the known planets, too distant and too faint to have been detected yet. This hypothetical object has been called Planet 9, Planet X, and half a dozen other names over the years. Its existence is not confirmed, its orbit is not known, but the orbits of the detached objects, clustered in ways that seem unlikely to be random, have convinced a growing number of astronomers that something massive is out there, tugging on the outer solar system in ways we cannot yet see directly. If Planet 9 exists, its gravity would shape the outer Kuiper Belt in ways that current models do not account for. It could shepherd objects into stable orbits at extreme distances. It could generate a population of small bodies that spend most of their time far beyond the classical Kuiper Belt, but occasionally drift close enough to produce the dust New Horizons is detecting. It could explain why the Kuiper Belt does not end cleanly at 50 astronomical units. And it could be the reason the outer solar system feels larger and more populated than we expected. The dust counter anomaly does not prove Planet 9 exists. It does not even prove the Kuiper Belt is significantly more extended than we thought. What it does is raise the possibility that we have been drawing the map of the outer solar system with incomplete information, sketching boundaries based on what we can see and assuming that what we cannot see does not matter. New Horizons is showing us that assumption was wrong. The region beyond 50 astronomical units is not empty. It is not quiet. Something is out there, and it is generating dust at a rate that does not match the models. The mission team has been analyzing the data for months, comparing it with theoretical predictions, trying to figure out what kind of population of objects would be needed to produce the observed dust density. The answer depends on how big the objects are, how fast they are colliding, and how much dust each collision produces. All of those parameters are uncertain. The size distribution of small Kuiper Belt objects is poorly known because objects smaller than about 50 kilometers across are too faint to detect from Earth. Collision rates in the outer Kuiper Belt are estimated from models, not measurements. And the amount of dust produced per collision depends on the composition and structure of the colliding bodies, which varies from object to object. Even with those uncertainties, the team has been able to put some rough numbers on what the dust data implies. To produce the observed dust density at 60 astronomical units, there would need to be a population of objects in that region comparable in total mass to the population in the classical Kuiper Belt, not identical, not the same size distribution, but comparable. That suggests the Kuiper Belt does not end at 50 astronomical units. It transitions. It thins out, yes, but it does not disappear. Objects keep orbiting out there, colliding, producing dust, existing in a part of the solar system we have barely begun to explore. This is not the first time a spacecraft has forced astronomers to revise their understanding of the outer solar system. When Voyager 1 crossed the heliopause, the boundary where the solar wind meets the interstellar medium, in 2012, it detected features in the plasma environment that did not match predictions. The boundary was more structured, more dynamic, and farther out than models had suggested. The same thing happened when Voyager 2 crossed the heliopause in 2018 at a different location. The two crossings were not identical. The heliopause was not a smooth spherical shell. It was lumpy, irregular, shaped by the motion of the Sun through the galaxy and the pressure of the interstellar wind pushing back against the solar wind. The Kuiper Belt may be similarly irregular. The classical picture, a smooth disk of objects thinning out gradually as you move away from Neptune, may be too simple. The real Kuiper Belt could be clumpy, with concentrations of material in some regions and voids in others. It could have structure on scales we have not resolved yet, shaped by gravitational resonances, planetary migration, and interactions with objects we have not discovered. The dust counter data is a hint that the reality is messier than the models, and messiness in science usually means there is more to learn. The student dust counter will keep recording data as long as New Horizons keeps functioning. The spacecraft is currently more than 60 astronomical units from the Sun and moving outward at about 3 astronomical units per year. By the late 2020s, it will be beyond 70 astronomical units, deeper into the outer solar system than any other human-made object except the 2 Voyager probes, which are heading in different directions and are no longer sending back usable science data. New Horizons is alone out there, the only functioning spacecraft in a position to measure the environment of the distant Kuiper Belt directly. Every dust grain it detects, every data point it transmits back to Earth, is a piece of information we have never had before. The spacecraft will eventually run out of power. Its plutonium generator is decaying, and by the mid-2030s, it will no longer produce enough electricity to keep the instruments running or the transmitter powered. When that happens, New Horizons will go silent. It will keep moving, coasting outward at more than 30,000 miles per hour, but it will no longer be able to tell us what it is seeing. The data it has already sent back, and the data it will send over the next decade, will be all we have until another mission is sent to the outer solar system. And given the time it takes to plan, build, and launch such a mission, that could be decades away. So the dust counter anomaly is not just a scientific curiosity, it is a reminder that the outer solar system is still largely unexplored. We have visited 2 objects in the Kuiper Belt up close, Pluto and Arrokoth. We have catalogued a few thousand more from ground-based telescopes, and that is it. The rest, the hundreds of thousands or millions of objects that models predict should be out there, remain invisible, known only through their collective gravitational influence and the faint traces of dust they produce as they collide. The boundaries of the solar system are not fixed. They shift as our instruments improve, as our spacecraft venture farther, and as our models become more sophisticated. 50 years ago, the edge of the solar system was Neptune. 30 years ago, it was Pluto. 20 years ago, it was the classical Kuiper Belt. Today, it is somewhere beyond 60 astronomical units, in a region we are only beginning to map. And tomorrow, it might be even farther out, pushed outward again by new data, new discoveries, and new questions that force us to admit how much we still do not know. The Kuiper Belt is not shrinking, it is expanding, not physically. It has always been the size it is. What is expanding is our awareness of it, our understanding of its scale and structure. And that expansion is uncomfortable because it means the solar system is larger, stranger, and more complex than we thought. The dust counter anomaly is a crack in the neat picture we had built. And cracks, once they appear, have a way of spreading, because if there is more dust out there than expected, and if that dust is evidence of a population of objects we have not accounted for, then what else have we missed? What other structures, populations, or features are hiding in the outer solar system, too faint to see and too far away to visit? And what happens when we finally get the tools to look more closely, when the next generation of telescopes comes online, or the next spacecraft is launched, and we discover that the Kuiper Belt is even larger and even stranger than the dust data suggests? The answer is that we will have to redraw the map again. We will have to revise the models, update the textbooks, and accept that the boundaries we thought were solid were just placeholders, temporary markers on a map that is still being filled in. The outer solar system is not finished revealing itself. The dust New Horizons is detecting is not an anomaly. It is a signal, a message written in microscopic particles of ice and rock, drifting through space at distances most people cannot imagine, telling us that the darkness beyond Neptune is not empty, it is full of objects we have not named, full of collisions we have not witnessed, full of stories we have not yet read. And somewhere out there, in that cold, immense unknown, there may be something else, something massive enough to shape the orbits of distant objects, something dark enough that we have never seen it, something that, if it exists, would explain not just the dust, but a whole collection of oddities in the outer solar system that have been quietly accumulating for years. Objects with orbits that do not make sense, clusters of detached bodies that should not be clustered, a gravitational signature with no visible source, a shadow in the data that grows darker the more closely we look. That shadow has a name, and it has been haunting astronomy for nearly a decade. The hunt for it has consumed careers, sparked debates, and driven missions, and the dust counter anomaly has just made it harder to ignore. Planet 9 does not exist, not officially. No one has photographed it, no spacecraft has visited it, no telescope has captured its light directly. It has no confirmed orbit, no measured mass, no known moons. It does not appear in any catalogue of solar system objects. The International Astronomical Union has not named it. NASA does not list it on any mission target roster. By every formal standard in astronomy, Planet 9 is not real, and yet a growing number of scientists are convinced it is out there, not because they want it to be, not because it would be exciting or convenient or good for grant proposals, though all of those things are true. They believe it because the mathematics say something massive is pulling on the outer solar system in ways that nothing we can see explains. The evidence is not direct. It is circumstantial, statistical, and maddeningly incomplete. But it is piling up, and the more data we collect from the distant Kuiper Belt, the harder it becomes to ignore the possibility that we are missing something enormous. This is the story of a planet that might not be there, and the objects whose orbits suggest it is. The hunt for Planet 9 begins with a different search entirely, one that had nothing to do with hidden planets and everything to do with mapping the edge of the known solar system. In the early 2000s, astronomers began systematically surveying the sky for distant objects beyond Neptune, using powerful ground-based telescopes and sensitive cameras capable of detecting extremely faint points of light. The goal was straightforward: Find Kuiper Belt objects, measure their orbits, build a catalogue, understand the structure of the outer solar system. What they found instead were outliers, objects so far out, with orbits so strange that they did not fit into any of the standard Kuiper Belt categories. These were not classical Kuiper Belt objects orbiting in neat circular paths between 40 and 50 astronomical units. They were not resonant objects locked in gravitational step with Neptune. They were not even typical members of the scattered disk, the population of bodies on elongated orbits that swing inward toward Neptune before heading back out. These objects were detached. Their closest approach to the Sun, their perihelion, was far beyond Neptune's influence, sitting at 60 or 80 or even 100 astronomical units. And their farthest point, their aphelion, stretched out to distances of several hundred astronomical units or more. Detached objects are rare. They are also deeply strange. To understand why, you need to understand how orbits work in the outer solar system. Neptune is the dominant gravitational force beyond Uranus. Its gravity shapes the orbits of nearly everything in the Kuiper Belt, either by scattering objects onto new paths or by locking them into stable resonances. If an object has a perihelion close to Neptune's orbit, around 30 astronomical units, Neptune's gravity can explain how it got onto its current trajectory. A close encounter with the planet sometime in the past could have flung it outward onto an elongated orbit. That is the standard explanation for the scattered disk. Those objects were kicked by Neptune. But detached objects never get close to Neptune. Their perihelia are too far out. Neptune's gravity weakens rapidly with distance, and by the time you are at 60 or 70 astronomical units, the planet's influence is negligible. It cannot scatter something that never comes near it, so the existence of detached objects raises an immediate question. What put them on those orbits? What kicked them outward if Neptune did not? For years, the answer was uncertain. Maybe they were scattered by Neptune early in the solar system's history when the planet was migrating outward through the primordial Kuiper Belt. Maybe they were perturbed by gravitational interactions with other large Kuiper Belt objects that have since been lost or ejected. Maybe they were influenced by a passing star billions of years ago. All of those explanations were plausible. None of them were satisfying. They required special circumstances, lucky timing, and a lot of assumptions about what the early solar system looked like. Then in 2014, astronomers discovered an object that made the problem worse. They named it 2014 VN112, and it was later given the nickname Biden. Biden's orbit is extreme. Its perihelion sits at about 80 astronomical units. Its aphelion stretches out to more than 900 astronomical units. For context, 900 astronomical units is roughly 30 times the distance from the Sun to Neptune. It is more than 20 times the distance to Pluto. At that distance, the Sun is not a disk. It is a bright star. No larger than Venus appears from Earth. The solar system, as most people imagine it, the region containing the planets and the Kuiper Belt and everything we have ever visited with spacecraft, is a small bright core surrounded by an enormous halo of darkness, and Biden spends most of its time in that halo. The discovery of Biden was not an isolated event. Other extreme Kuiper Belt objects, sometimes called EKBOs, were found in the years that followed. Each one had a similarly bizarre orbit, swinging far beyond the known solar system before looping back toward the Sun. And as more of these objects were catalogued, a pattern began to emerge. Their orbits were not random, they were clustered. The clustering showed up in several ways. First, the perihelia of the extreme objects, the points where they come closest to the Sun, were grouped together in a relatively narrow range of distances. Most of them had perihelia between 50 and 80 astronomical units. even though their aphelia varied wildly. Second, the orientations of their orbits were similar. Orbits in space are defined by several parameters, including inclination, the tilt relative to the plane of the solar system, and argument of perihelion, which describes where the closest point of the orbit sits relative to the rest of the solar system. For most solar system objects, those parameters are distributed more or less randomly, but the extreme Kuiper Belt objects were different. Their orbits were aligned, not perfectly, but enough that the alignment was statistically noticeable. Third, and most strikingly, the long axes of their orbits, the lines connecting perihelion to aphelion, pointed in roughly the same direction. If you drew all of their orbits on a map of the solar system, the long axes would cluster together in a narrow cone pointing away from the Sun. That kind of alignment is not something you expect to see by chance. Orbits precess over time, slowly rotating like the hands of a clock, and over millions or billions of years they should spread out and point in all directions. The fact that these orbits were still clustered suggested something was holding them in place, shepherding them into a preferred configuration. In 2016, two astronomers at the California Institute of Technology, Konstantin Batygin and Mike Brown, published a paper in the Astronomical Journal arguing that the clustering could be explained by the gravitational influence of an unseen planet, not a small planet, a large one. They estimated it would need to be roughly 10 times the mass of Earth, comparable in size to Neptune, and orbiting at an average distance of several hundred astronomical units from the Sun. The orbit would be highly elongated, swinging from perhaps 200 astronomical units at perihelion to as much as 1,000 astronomical units or more at aphelion. And it would be tilted relative to the plane of the solar system, inclined at an angle of perhaps 15 to 25 degrees. They called it Planet 9. The name was deliberate. It was a callback to the Planet X searches of the early 20th century, the hunt that had led to the discovery of Pluto. But it was also a statement. If this planet exists, it is the 9th planet, reclaiming the spot Pluto lost when it was reclassified as a dwarf planet in 2006. The paper did not claim to have discovered Planet 9. It claimed to have found evidence that it should exist, based on the orbits of known objects and the physics of how gravity shapes those orbits over long timescales. The reaction was immediate and divided. Some astronomers found the argument compelling. The clustering was real. The statistics were solid. The odds of seeing that kind of alignment by chance, assuming there was no hidden planet, were low. Estimates varied, but most analyses put the probability somewhere between 1 in a few hundred and 1 in a few thousand. Not impossible, but unlikely enough to take seriously. Other astronomers were skeptical. The sample size was small, fewer than a dozen extreme Kuiper Belt objects with well-measured orbits. Small samples are prone to statistical flukes, and the objects themselves were discovered by surveys that did not cover the entire sky uniformly. If the surveys were biased towards certain regions, the apparent clustering could be an artifact of where astronomers happened to look, rather than a real feature of the outer solar system. The debate has continued for nearly a decade. New objects have been discovered. New analyses have been published. Some support the Planet 9 hypothesis. Others argue the clustering is weaker than it appears, or that alternative explanations such as the combined gravitational influence of many smaller objects could produce similar effects without requiring a single massive planet. The statistical significance of the clustering has been recalculated dozens of times, and depending on which objects you include, which parameters you measure, and how you account for observational bias, the answer changes. What has not changed is the basic structure of the argument. If you take the orbits of the most extreme Kuiper Belt objects at face value, Something massive appears to be tugging on them. That something could be a planet, it could be something else, but it is hard to look at the data and conclude that nothing is happening. The physics of how Planet 9 would shape the outer solar system are well understood. A massive planet on a distant eccentric orbit exerts gravitational forces on nearby objects that vary depending on where the planet is in its own orbit. When the planet is at perihelion, closer to the Sun, its gravity pulls on objects in the inner part of its orbital neighborhood, nudging them into specific configurations. When it is at aphelion, farther out, it influences a different set of objects. Over millions of years, those nudges add up. Objects that start on random orbits get sorted into groups. Some are pushed into orbits that align with the planet's orbit. Others are scattered onto paths that avoid the planet entirely. The end result is a population of objects with clustered orbital parameters, exactly the kind of pattern seen in the extreme Kuiper Belt. Computer simulations of this process have been run by multiple research groups, and the results consistently show that a Neptune-mass planet on a distant orbit can produce the observed clustering. The simulations also make predictions. They suggest that Planet 9, if it exists, should have scattered some objects onto orbits that are nearly perpendicular to the plane of the solar system, looping up and over the rest of the planets before diving back down. A few objects like that have been found, which strengthens the case. The simulations also predict that there should be a population of objects on orbits that are anti-aligned with the extreme Kuiper Belt objects, pointing in the opposite direction. Those have not been found yet, but that could be because they spend most of their time at extreme distances where surveys have not looked carefully. So where is it? If Planet 9 is real, and if it is as massive as the models suggest, why has no one seen it? Distance and brightness. A planet at several hundred astronomical units is extraordinarily faint. It receives almost no sunlight. What little light does reach it reflects back toward Earth so weakly that even the largest telescopes struggle to detect it. The brightness of a planet falls off with the fourth power of its distance from the Sun. Move twice as far away, and the planet appears 16 times dimmer. Move 10 times farther, and it is 10,000 times dimmer. At 300 astronomical units, Planet 9 would be roughly 100 million times fainter than Neptune appears from Earth. Neptune itself is barely visible to the naked eye under ideal conditions, and it sits at 30 astronomical units. Planet 9, if it is out there, is invisible to everything except the most sensitive wide-field surveys. The search has been ongoing for years. Mike Brown, one of the original proponents of the Planet 9 hypothesis, has been using the Subaru telescope in Hawaii to scan large areas of the sky, looking for faint moving objects. Other teams have used different telescopes and different strategies. The challenge is not just finding a faint point of light. It is distinguishing that point of light from the millions of other faint points of light in the same region of sky, most of which are distant stars or galaxies that are not moving. Planet 9, if it is there, moves slowly because it is so far from the Sun and because its orbital speed is low. Over the course of a single night, it might shift by only a tiny fraction of a degree. To detect that motion, you need multiple images of the same patch of sky taken over weeks or months, and you need software capable of comparing those images and picking out the one object that moved while everything else stayed still. The search is also complicated by the fact that we do not know exactly where Planet 9 is in its orbit. The models predict a general region of sky where it is most likely to be, but that region is still enormous, covering thousands of square degrees. Scanning that much sky to the necessary depth takes time, and if Planet 9 happens to be near aphelion, the farthest point in its orbit, it could be more than twice as far away as the models initially suggested, making it correspondingly fainter and harder to find. There is also the possibility that Planet 9 is not a planet at all. One alternative hypothesis suggests it could be a primordial black hole, a tiny black hole left over from the early universe with a mass of about 5 to 10 Earth masses. Primordial black holes are hypothetical. We have never detected one. But if they exist, they would produce gravitational effects identical to a planet of the same mass, while being far too small and dark to see directly. The only way to detect a primordial black hole in the outer solar system would be through its gravitational influence, or through the faint glow of Hawking radiation, which for a black hole of this size would be undetectable with current instruments. The primordial black hole idea has not gained widespread support, but it is a reminder that Planet 9, if it exists, might not look like what we expect. It might not be a rocky super-Earth or an ice giant. It could be something stranger, a captured rogue planet that formed around a different star and was grabbed by the sun's gravity as it drifted through interstellar space. Or it could be a failed core, the beginning of a giant planet that never finished forming because it ran out of material to accrete. Any of those scenarios would produce the same gravitational signature. None of them would make the planet easier to find. The statistical debate over whether Planet 9 is necessary continues to evolve. Some recent analyses have suggested that when you account for observational biases, the clustering of extreme Kuiper Belt object orbits is less significant than it initially appeared. Surveys tend to find more objects in certain parts of the sky simply because those regions have been observed more often or with better instruments. If you correct for that bias, the clustering weakens. Other analyses have argued that the bias corrections themselves are flawed and that the clustering remains statistically significant even after accounting for how the objects were discovered. This is messy science. There is no smoking gun. There is no single piece of evidence that proves Planet 9 exists. What there is instead is a collection of orbital oddities that are hard to explain without invoking something we have not seen. And the more extreme Kuiper Belt objects we find, the harder it becomes to dismiss the pattern as noise. One of the most compelling pieces of evidence is an object called Sedna, discovered in 2003, years before the Planet 9 hypothesis was proposed. Sedna's orbit is one of the most extreme known. Its perihelion is about 76 astronomical units, and its aphelion stretches to more than 900 astronomical units. The orbit takes roughly 11,000 years to complete. Sedna never comes close to Neptune, which means Neptune could not have scattered it onto its current path. And Sedna's orbit is too stable to have been shaped by a passing star, unless that star came close enough to the Sun to disrupt the orbits of the inner planets, which we know did not happen. Planet 9, if it is real, offers a clean explanation for Sedna. A distant, massive planet could have nudged Sedna onto its current orbit over millions of years without requiring any special events or close encounters. The same explanation works for Biden and for the other extreme objects that have been found since. One planet, one gravitational influence, solves multiple puzzles at once. That elegance is appealing. It does not prove the hypothesis is correct, but it makes the hypothesis hard to dismiss. The search for Planet 9 has also been aided by the development of new observatories and survey programs designed to scan the sky more efficiently. The Vera Rubin Observatory, scheduled to begin full operations in the mid-2020s, will conduct the Legacy Survey of Space and Time, a 10-year program that will image the entire visible sky every few nights. The survey is expected to discover tens of thousands of new Kuiper Belt objects, including many extreme objects that have been too faint to detect with current instruments. If Planet 9 is there, and if it is anywhere near the predicted region of sky, the Rubin Observatory should find it. Future space telescopes may also contribute to the search. The Nancy Grace Roman Space Telescope, set to launch later this decade, will have a wide field of view and high sensitivity in the infrared, making it well suited for detecting faint, distant objects. And if Planet 9 is particularly far away or particularly dark, it might not show up in reflected sunlight at all. Instead, it might emit faint thermal radiation, heat left over from its formation, and that radiation would be easier to detect in the infrared than in visible light. The possibility that Planet 9 does not exist is real. It is entirely possible that the clustering of extreme Kuiper Belt objects is a coincidence, a statistical fluke that will dissolve as more objects are discovered and the sample size grows. It is possible that the orbits are being shaped by something other than a single planet, a swarm of smaller objects, or a more complex dynamical process that we do not yet understand. And it is possible that our models are wrong, that the simulations are missing some key piece of physics that would explain the observed orbits without requiring a hidden planet. But the possibility that it does exist is also real. And if it is real, the implications are staggering. The solar system would be larger than we thought, the inventory of planets would be incomplete, and there would be an entire world, larger than Earth, sitting in the outer darkness, too far away to have been noticed by any civilization until ours. A planet that has been there since the beginning, orbiting silently, shaping the outer solar system in ways we are only now beginning to recognize. The hunt for Planet 9 is not just about finding a new planet. It is about understanding the architecture of the solar system, the forces that shaped it, and the structures that still exist at its edges. The extreme Kuiper Belt objects are messengers, carrying information about what lies beyond the regions we have explored. Their orbits are clues, and those clues point towards something massive, something distant, and something that should not be there unless we have been drawing the map of the solar system with a blank spot where a planet belongs. The search continues. Telescopes scan the sky. Computers sift through images. Models refine their predictions. And somewhere out there, in the cold, immense darkness beyond Neptune, Planet 9 either waits to be found or does not exist at all. The answer will come eventually, whether from a new detection, a new survey, or a statistical analysis that finally closes the debate. Until then, the outer solar system remains larger and stranger than we can confirm, shaped by forces we can measure but not yet see, and haunted by the possibility that we are not finished discovering what orbits our sun. And if we are not finished discovering planets, then we are certainly not finished discovering what else might be out there. Because even if Planet 9 is not real, the Kuiper Belt is. Its objects are real. Their compositions are real. And some of those compositions are so volatile, so unstable, and so chemically active that they should not be able to hold on to atmospheres at all, and yet they do. So the search for Planet 9 continues. Telescopes scan the darkness, models refine their predictions, computers sift through mountains of data looking for a faint point of light that moves where everything else stays still. And somewhere in that same darkness, scattered among the millions of icy bodies drifting beyond Neptune, there are objects we have barely begun to understand. Objects that, by every rule we have written about how small worlds behave, should be dead, frozen solid, chemically inert, atmospherically barren. Most of them are. But what if one of them is not? This is not a story about something we have found, not yet. This is a story about something we might find. A scenario that sits just on the edge of plausible, grounded in real physics and real chemistry, waiting for the right telescope to point at the right patch of sky at the right moment. It is a story about what happens when the rules we thought were solid turn out to have exceptions. And it starts with a simple question. Can a tiny Kuiper Belt object have an atmosphere? The answer, according to everything we know about small icy bodies in the outer solar system, should be no. Atmospheres require specific conditions. You need enough gravity to hold on to gas molecules and prevent them from drifting into space. You need a source of those gases, something that replenishes the atmosphere faster than it leaks away. And you need temperatures cold enough that volatile materials, things like nitrogen and methane and carbon monoxide, do not boil off immediately when they reach the surface. Small objects fail most of those tests. Their gravity is weak. Their interiors are cold. And even in the Kuiper Belt, where the average temperature hovers around 50 Kelvin, roughly minus 220 Celsius, solar radiation and cosmic rays are constantly stripping away any tenuous envelope of gas that tries to form. The Kuiper Belt is full of small objects, hundreds of thousands of them larger than 100 kilometers across, millions more smaller than that. Most of them are inert chunks of ice and rock, remnants of the material that built the outer planets, sitting in stable orbits that have not changed significantly in billions of years. They do not have atmospheres. They do not have geological activity. They are cold, dark, and quiet. The occasional impact chips away at their surfaces. Cosmic rays slowly darken their ices into complex organic compounds. But nothing moves, nothing flows, nothing changes on timescales shorter than millions of years. The exceptions are well known. Pluto has an atmosphere, thin, fragile, prone to collapsing and freezing out when Pluto swings too far from the Sun, but real, measurable. Pluto is large enough, roughly 2/3 the diameter of Earth's moon, that its gravity can hold on to nitrogen gas when the surface warms and that nitrogen sublimates. Eris, another large dwarf planet, likely has a similar atmosphere, though we have never measured it directly. Makemake and Quaoar, both smaller than Pluto but still massive compared to most Kuiper Belt objects, may have thin seasonal atmospheres as well. All of these are at the upper end of the size distribution. Worlds large enough to have retained some internal heat, large enough to generate geological activity, large enough that their gravity can compete with the forces trying to strip their atmospheres away. But a small Kuiper Belt object, something a few hundred kilometers across or smaller, should not be able to hold an atmosphere. The gravity is too weak. The surface area relative to volume is too high, which means heat leaks away faster. There is no tidal heating because these objects are not locked in gravitational resonances with massive planets. There is no radiogenic heating to speak of because small bodies do not contain enough radioactive material to generate meaningful warmth. They froze early in their history and stayed frozen. That is the rule. That is what the models say. That is what every observation of small Kuiper Belt objects has confirmed. Now imagine a new telescope. Not Hubble, not Webb. Something built in the late 2020s, designed specifically to study faint distant objects with unprecedented sensitivity. A space-based observatory with a large mirror. A suite of spectrographs capable of splitting incoming light into its component wavelengths with extraordinary precision, and enough observing time to stare at individual Kuiper Belt objects for hours or days, collecting photons one by one until a spectrum emerges. The kind of instrument that can detect not just the reflected sunlight bouncing off an icy surface, but the faint absorption lines that indicate gas molecules floating above that surface, blocking specific wavelengths of light as they pass between the object and the telescope. Imagine the telescope points at a small Kuiper Belt object, not one of the famous ones, not Pluto or Eris or Arrokoth. Something smaller, something recently discovered in a survey, orbiting at about 55 astronomical units from the Sun. A body may be 200 kilometers across, roughly the size of a mid-sized asteroid, unremarkable in every measurable way. Faint, distant, cold. The telescope collects light for several days, long enough to build up a spectrum with enough signal to analyze. The data comes down. The team processes it. And there, buried in the noise but statistically significant, are absorption lines. Nitrogen, methane, carbon monoxide. The spectral signatures are unmistakable. This object has an atmosphere. That would be the moment everything stops making sense. A 200-kilometer Kuiper Belt object should not be able to hold on to an atmosphere. The escape velocity, the speed a gas molecule needs to reach to break free of the object's gravity, is low. For a body that size, it is somewhere around 100 meters per second, maybe less depending on the density. Gas molecules at 50 Kelvin are moving slowly, but they are still moving. Nitrogen molecules at that temperature have an average speed of about 200 meters per second. Half of them are moving faster than that. Some are moving much faster. Over time, the fastest molecules escape. The atmosphere leaks away. Without a constant source replenishing it, the gas should be gone within a few thousand years, maybe a few million if the object is particularly cold and the escape rate is slower than expected, but not billions of years, not over the entire history of the solar system. So if the atmosphere is there, something is putting it there, continuously, right now. The immediate reaction among planetary scientists would be skepticism. Atmospheres on small bodies have been claimed before and turned out to be observational artifacts, misinterpreted data, or transient phenomena that disappeared when better instruments looked more carefully. The first thing the team would do is check the calibration, reprocess the data, look for contamination in the signal, confirm that the absorption lines are real and not just noise that happens to look like nitrogen or methane. Assuming the signal holds up, the next step is to measure the density. How much gas is actually there? The answer would almost certainly be not much. A small object with weak gravity cannot hold onto a thick atmosphere. What we would be looking at is more like an exosphere, a tenuous haze of gas molecules barely clinging to the surface, with a density millions of times lower than Earth's atmosphere. But even a tenuous atmosphere is an atmosphere. It means gas is escaping the surface. It means something is generating that gas. And it means the object is not dead. The composition matters. Nitrogen, methane, and carbon monoxide are all volatile ices commonly found in the Kuiper Belt. They freeze solid at the low temperatures out there, coating the surfaces of most objects as thin layers of frost. If the temperature rises even slightly, those ices can sublimate, turning directly from solid to gas without melting in between. The process is the same one that creates the glowing tails of comets when they swing close to the sun and their ices start to boil off. On a Kuiper Belt object far from the sun, the sublimation rate would be much slower, but it would not be zero. Even at 50 Kelvin, some fraction of the ice molecules on the surface have enough thermal energy to break free and drift upward into the space above the object. Under normal circumstances, that gas would escape almost immediately. The object's gravity is too weak to hold it. Solar radiation would ionize the molecules, and the solar wind would blow them away. Over a few thousand years, maybe a few tens of thousands, the surface would lose its volatile ices entirely, leaving behind only the less volatile materials like water ice and rock. Most small Kuiper Belt objects have probably gone through this process already. They formed with volatile ices on their surfaces, but over billions of years those ices sublimated away, and what remains now is a darker, older, less chemically interesting surface. But if a small object still has an atmosphere, it means the volatile ices are still there, still sublimating. still replenishing the thin envelope of gas faster than it escapes. That requires an explanation. The first possibility is sustained cryovolcanism. Cryovolcanoes are volcanoes that erupt not molten rock, but a slurry of water, ammonia, methane, and other icy materials mixed with dissolved gases. They exist on several moons in the outer solar system. Enceladus, one of Saturn's moons, has active cryovolcanoes at its south pole that spray plumes of water vapor and organic molecules into space. Triton, Neptune's largest moon, has geysers that erupt nitrogen gas. Both of those moons are larger than a 200-kilometer Kuiper Belt object, and both are heated by tidal forces from their host planets, forces that do not exist for an isolated object drifting through the Kuiper Belt. But the mechanism, the basic idea that internal heat can drive the release of volatiles from beneath the surface, is well understood. If the small Kuiper Belt object were cryovolcanically active, it would mean something inside it is warm, not hot, not molten, but warm enough that pockets of volatile-rich ice can melt or soften, creating pathways for gas to escape through cracks in the crust. The gas would vent to the surface, sublimate, and form an atmosphere. As long as the venting continues, the atmosphere persists. The challenge is explaining where the heat comes from. Small objects cool quickly. There is not enough radioactive material in their interiors to sustain geological activity over billions of years. Tidal heating is not an option unless the object is part of a binary system, gravitationally locked to a companion object in a close orbit. And even then, the amount of tidal heating generated by a pair of small Kuiper Belt objects would be minimal. One speculative possibility is that the object formed recently, not in the sense that it coalesced from the protoplanetary disk a few million years ago. That would contradict everything we know about solar system formation, but in the sense that it was created by a collision. Two larger Kuiper Belt objects smashed into each other at some point in the relatively recent past, maybe a few million years ago, and the small object we are looking at now is a fragment, a piece that broke off, still warm from the energy of the impact, still outgassing volatiles that were buried inside the parent bodies before the collision exposed them. If that is the case, the atmosphere would be transient. It would last for a few million years, maybe tens of millions, and then it would fade as the object cooled and the outgassing slowed. We would be seeing it during a brief window when it is still active, before it settles into the same cold, inert state as every other small object in the Kuiper Belt. Another possibility is trapped volatiles. Imagine that when the object formed, it incorporated large amounts of volatile ices deep in its interior. Water ice on the surface insulated those volatiles, keeping them from sublimating away over the first few billion years of the solar system's history. Then, sometime relatively recently, a crack opened. Maybe a small impact fractured the crust. Maybe thermal stress, the slow expansion and contraction of the ice as the object's orbit carried it closer to and farther from the sun, created a weak point. The crack allowed gas to escape from the interior, slowly bleeding out through the fissure, creating a thin atmosphere fed by the reservoir of trapped volatiles below. This scenario does not require ongoing internal heat. It just requires a pathway for the gas to reach the surface. A third possibility is seasonal warming. The object's orbit, like most Kuiper Belt orbits, is probably not perfectly circular. It is at least slightly elliptical, which means the distance from the Sun varies over the course of one complete orbit. When the object is at perihelion, the closest point to the Sun, it receives slightly more sunlight than it does at aphelion, the farthest point. The difference is small, a few percent at most, but that might be enough to cause seasonal sublimation of surface ices. At perihelion, nitrogen and methane ices warm just enough to release gas, thickening the atmosphere. At aphelion, the gas condenses and freezes back onto the surface. If the orbit takes hundreds or thousands of years to complete, we might be seeing the object near perihelion during the brief period when its atmosphere is at its thickest. None of these explanations are entirely satisfying. Each one requires special circumstances, lucky timing, or assumptions about what the object's interior looks like that we cannot verify without sending a spacecraft there, and yet one of them, or something like them, would have to be true if the atmosphere is real. Because the alternative, that small Kuiper Belt objects can sustain atmospheres over billions of years without any special conditions, would break the rules in ways that are hard to reconcile with the physics. The discovery would spark immediate debate. Papers would be published within months. Some would argue that the detection is real and represents a new class of active Kuiper Belt object that we did not know existed. Others would argue that the signal is marginal, that the absorption lines are not strong enough to rule out other explanations, and that the whole thing is being overhyped. Follow-up observations would be scheduled. Other telescopes would be tasked with looking at the same object, or at similar objects, to see if the atmosphere is unique or if there are others like it that we have simply never looked at closely enough to notice. If the atmosphere turns out to be real and if similar atmospheres are detected on other small Kuiper Belt objects, it would force a rethinking of what counts as an active world. Activity in planetary science usually means geological processes, volcanoes, tectonics, convection, ice flows, atmospheres. The assumption has always been that small bodies are too cold, too dead, to support any of those processes. The discovery of an atmosphere on a small Kuiper Belt object would suggest that the line between active and inactive is not as sharp as we thought. It would mean that even at extreme distances, even on bodies with negligible internal heat, chemistry can still happen, gases can still be released, surfaces can still change. The implications for habitability are harder to pin down. An atmosphere alone does not make a place habitable. The Kuiper Belt is cold, the objects are small, there is no liquid water on the surface. There is no obvious energy source to drive the complex chemistry that life as we know it requires. But habitability is not a binary, it is a spectrum, and every time we push the boundaries of where active geology can occur, we expand the range of environments where we might, in principle, find conditions that support some form of chemistry more complex than we expected. Life in the Kuiper Belt is not plausible by any current model. The energy is too low, the temperatures are too cold, the timescales are too slow. But 20 years ago, the idea of a subsurface ocean on Enceladus was not plausible either. 30 years ago, the idea of active geology on Pluto was dismissed as unlikely. The history of planetary science is full of moments when something we thought was impossible turned out to be merely improbable. And improbable things happen all the time when you have hundreds of thousands of objects to choose from and billions of years for unlikely events to occur. The real value of discovering an atmosphere on a small Kuiper Belt object would not be in proving that life exists there. It would be in proving that we do not understand the Kuiper Belt as well as we thought we did. It would force us to ask new questions. How common are these atmospheres? What drives them? How long do they last? Are there other small objects with similar features that we have not detected yet because we have not looked carefully enough? And if small objects in the Kuiper Belt can be geologically active, even transiently, what does that mean for the billions of similar objects that must exist in other planetary systems around other stars? The Kuiper Belt is not just a collection of frozen debris, it is a laboratory, a place where the processes that built the planets are still visible, preserved in the orbits and compositions of objects that have not been disturbed since the solar system formed. Every new discovery in the Kuiper Belt, every object that defies expectations, is a clue about how planetary systems evolve, how materials are distributed in the outer reaches of a star's influence, and how far from a star you can go before the conditions become so extreme that nothing interesting happens anymore. An atmosphere on a small Kuiper Belt object would push that boundary outward. It would suggest that the transition from active to inactive, from chemically dynamic to geologically dead, is not a hard line drawn at a specific distance from the Sun or a specific size of object. It would mean that the Kuiper Belt, even at its coldest and most distant edges, is still capable of surprising us. And if the Kuiper Belt can surprise us, then the regions beyond it, the scattered disk and the Oort cloud, and the vast empty space between the solar system and the nearest stars might hold surprises of their own. This is not a discovery that has happened yet. It might never happen. The speculative scenario depends on finding an object that is rare, observing it with an instrument that does not yet exist, and detecting a signal that might be too faint to measure, even with the best telescopes we can build. But the possibility is real. The physics allows it. The chemistry allows it. And the Kuiper Belt is large enough, diverse enough, and strange enough that somewhere out there, among the millions of objects we have never looked at closely, there might be one that refuses to follow the rules. The search for Planet 9 is a hunt for something massive, something that shapes the architecture of the outer solar system through sheer gravitational dominance. The hunt for an atmosphere on a small Kuiper Belt object is a hunt for something subtle, something that whispers rather than shouts, something that exists at the edge of what our instruments can detect and our models can explain. Both hunts are driven by the same impulse, the need to know what is out there, the need to map the edges of our solar system, not just in terms of distance, but in terms of activity, complexity, and the potential for processes we have not yet imagined. And both hunts remind us that the solar system is not finished revealing itself. The Kuiper Belt is not a graveyard. It is not a museum. It is a frontier, and the frontier is still moving. Every new telescope, every new mission, every new dataset pushes the boundary a little farther out, into regions that were invisible a decade ago and will be routine a decade from now. The objects we are finding today were always there. They were always orbiting, always colliding, always sublimating and outgassing and evolving in ways we could not see because we were not looking closely enough. Now we are looking. And the more we look, the more we realize how much we have missed. The discovery of an atmosphere on a small Kuiper Belt object, if it happens, will not be the end of the story. It will be the beginning of a new one. A story about what it means for a small icy world to be active. A story about how far from the Sun geological processes can persist. A story about the chemistry that happens in the coldest, darkest, most isolated corners of the solar system, and whether that chemistry is simple or complex, brief or sustained, unique or common. It will be a story that forces us to redraw the map again, to add another layer of detail to a region we thought we understood, and to admit that the edges of the solar system are not where we thought they were. Not geographically, not chemically, and not in terms of what counts as a world worth paying attention to. The atmosphere, if it exists, is a signal, a faint one, buried in noise, easy to miss and hard to interpret. But signals are what astronomy is built on, faint points of light that turn out to be galaxies, tiny wobbles in stellar spectra that turn out to be planets, small shifts in orbital parameters that turn out to be the fingerprints of unseen companions. The Kuiper Belt is full of signals, most of them we have not detected yet. Some of them we have detected but not understood. And somewhere in that noise, there might be a signal telling us that even the smallest, coldest, most isolated objects in the solar system are not as dead as we assumed. They are waiting. And if we look closely enough, they will tell us what they are made of, where they came from, and what they are still capable of becoming. So we have traveled more than 5 billion miles from the chair you are sitting in, and we are still not done. We have seen Pluto, a world that was supposed to be dead, turn out to have a beating heart, smooth plains of nitrogen ice, churning like a pot of boiling water, slowed down by a factor of millions, mountains of frozen water floating in seas of frozen nitrogen, a subsurface ocean that might still be liquid beneath kilometers of ice. We have seen Arrokoth, two ancient lobes that drifted together at walking speed 4.5 billion years ago and stuck, preserving the conditions of the early solar system in a shape so pristine it looks like it was frozen yesterday. We have mapped the Kuiper Belt, a structure so vast that calling it a belt feels inadequate. A disk of icy debris stretching billions of miles in every direction, thinning as it goes but never quite disappearing, blending into the scattered disk and the detached objects and the gravitational shadows that suggest something even larger is hiding in the dark. And every single one of those discoveries has forced us to redraw the map. Not just add details to the edges, redraw it. The solar system we thought we knew, the neat row of planets with a few asteroids in between and maybe some comets wandering through on long elliptical paths, is not the solar system we live in. The real solar system is messier, larger, and stranger. The boundaries we drew were placeholders, temporary markers on a map that was still being filled in. And the more we fill it in, the more we realize how much blank space is left. The Kuiper Belt is not the edge of the solar system. It is the beginning of the edge. The place where the familiar neighborhood, the region where sunlight is bright enough to warm surfaces and drive weather and make atmospheres behave in predictable ways, gives way to something colder, darker, and more isolated. Beyond the Kuiper Belt lies the scattered disk, a population of objects on orbits so elongated that they spend most of their time hundreds of astronomical units from the Sun, swinging inward only briefly before retreating into the void. Beyond the scattered disk lies the inner Oort cloud, a theoretical shell of icy bodies that has never been directly observed, but whose existence is inferred from the orbits of long-period comets that fall into the inner solar system from seemingly random directions. And beyond the inner Oort cloud lies the outer Oort cloud, a spherical halo of trillions of objects stretching halfway to the nearest star, so diffuse and so distant that it would take tens of thousands of years for a spacecraft traveling at New Horizons speed to cross it. That is the solar system. Not 8 planets and a handful of moons, not a disk a few billion miles wide with the Sun at the center. A structure that begins with Mercury hugging the Sun at a distance of 36 million miles and extends outward to roughly 2 light-years, the estimated outer boundary of the Oort cloud, where the Sun's gravity finally loses its grip and objects drift into interstellar space. 2 light-years. That is more than 100,000 astronomical units. That is more than 100 trillion miles. If you built a scale model of the solar system where the Earth was the size of a marble, the outer edge of the Oort cloud would be more than 4 miles away, and most of that space, the vast majority of it, is empty, dark, cold, populated by objects we will never see and probably never name. The Kuiper Belt sits at the inner edge of that darkness. It is the last region of the solar system where objects are close enough and numerous enough that we can study them in any detail. Beyond it, the distances become so extreme and the objects so faint that even our most powerful telescopes struggle to detect them. And yet the Kuiper Belt itself was invisible to us until the 1990s. We built telescopes, we launched spacecraft, we mapped the planets and their moons, and for decades we looked right past the Kuiper Belt because it was too faint, too far away, and too unexpected. Nobody was looking for it because nobody believed it was there. That is the first lesson the Kuiper Belt teaches us. The solar system is not what we assume it is. It is what the data says it is, and the data has been telling us for the last 30 years that our assumptions were wrong. We assumed the solar system ended at Neptune because that was the last planet we could see. We assumed small icy worlds were geologically dead because we had never visited one up close. We assumed the outer solar system was quiet, stable, and unchanging because we did not have the instruments to detect the activity that was happening out there. Every one of those assumptions has been overturned, not by speculation or theory, but by observation. By pointing telescopes at the right patches of sky and waiting long enough for the signal to emerge from the noise. The second lesson is about scale. The Kuiper Belt is roughly 4.5 billion miles wide. That number is so large it stops meaning anything unless you force yourself to sit with it. 4.5 billion miles is the distance light travels in about 6.5 hours. It is more than 300 times the distance from the Earth to the Sun. It is wide enough that if you could somehow stand at one edge and look across to the other, the objects on the far side would be invisible, too faint and too far away to see even if you had perfect vision and a perfect vacuum. And yet the Kuiper Belt is not empty. It is full. Hundreds of thousands of objects larger than 100 kilometers across. Millions more smaller than that. A total mass that might once have been tens of Earth masses before planetary migration and collisions and billions of years of erosion ground most of it down and scattered it away. We have catalogued about 2,000 Kuiper Belt objects so far. 2,000 out of hundreds of thousands, maybe millions. We have visited two of them up close, Pluto and Arrokoth. That is the extent of our direct exploration. Everything else we know about the Kuiper Belt comes from telescopes, from ground-based surveys that scan tiny patches of sky looking for faint moving dots, from spectrographs that measure the light reflecting off distant surfaces and deduce what those surfaces are made of. We are mapping a region the size of the inner solar system using instruments that can barely resolve individual objects, and the map we are building is full of gaps, large gaps, entire populations of objects that we know must be there because the models say so, but that we have never detected because they are too small, too dark, or too far away. The third lesson is about time. The Kuiper Belt is old. Not just old in the sense that it has been there for billions of years, old in the sense that it is a record of what the solar system looked like when it was young. The objects in the Kuiper Belt are leftovers, pieces of the original material that built the planets, preserved in the deep freeze of the outer solar system because they never got close enough to the sun to be altered by heat, never got swept up into planets, and never collided violently enough to be shattered or melted. Arrokoth is the clearest example of this. A contact binary, two lobes that formed separately and merged gently, sitting in an orbit that has not changed significantly in 4.5 billion years. Its surface is coated in organic molecules that have been slowly darkening over billions of years as cosmic rays break apart simple ices and reassemble them into more complex compounds. It is red. Very red. The reddest object New Horizons has ever visited. And that color is not paint. It is time. 4.5 billion years of it, written in chemistry, preserved in ice. Every object in the Kuiper Belt is a time capsule, not metaphorically, literally. They contain information about the early solar system that exists nowhere else. The planets have been resurfaced by volcanism, tectonics, and impacts. The asteroids have been battered and heated and broken apart. The comets that fall into the inner solar system have been altered by repeated passes near the Sun, losing their volatile ices and leaving behind rocky cores. But the Kuiper Belt objects have stayed cold, stayed distant, stayed intact. They are samples of the protoplanetary disk, the cloud of gas and dust that surrounded the newborn Sun 4.5 billion years ago, and they have not been significantly altered since. That makes them scientifically invaluable. It also makes them impossible to study in any detail without sending spacecraft there, and spacecraft are expensive, slow, and limited in what they can carry. New Horizons took 9.5 years to reach Pluto. It spent a few hours in Pluto's neighborhood, collected as much data as its instruments could hold, and kept going. The data it sent back has kept scientists busy for nearly a decade, and they are still finding new things in it, still refining models, still arguing about what the images and spectra actually mean. A single flyby of a single object generated years of work. There are hundreds of thousands of objects in the Kuiper Belt. We will never visit more than a handful of them. The rest will remain distant, faint, and largely unknown, studied only through the indirect methods we have available. Ground-based telescopes, space telescopes, computer models, inferences drawn from the orbits and compositions of the objects we can see, extrapolated outward to the populations we cannot. The fourth lesson is about gravity. The Kuiper Belt is shaped by forces we cannot see. Neptune is the most obvious one. Its gravity dominates the inner Kuiper Belt, locking objects into resonances, scattering others onto unstable orbits, carving out gaps where objects used to be but can no longer survive. The classical Kuiper Belt, the region between about 42 and 48 astronomical units, is what remains after Neptune finished migrating outward and clearing out the inner edge. The scattered disk, the population of objects on wild elongated orbits, is the debris field left behind by that migration. Objects that had close encounters with Neptune billions of years ago and were flung outward into the darkness. But Neptune is not the only gravitational force at work. There are hints, growing stronger with every new object we discover, that something else is out there, something massive. Planet 9, if it exists, would be a Neptune-mass object orbiting at several hundred astronomical units from the Sun, far beyond the classical Kuiper Belt, in a region where direct detection is extraordinarily difficult. Its existence is inferred from the orbits of extreme Kuiper Belt objects, bodies that swing out to distances of several hundred or even 1,000 astronomical units before looping back toward the Sun. Those orbits are clustered in ways that are hard to explain without invoking a massive unseen perturber. The clustering is not perfect. The statistics are not conclusive. But they are suggestive, and they have been getting more suggestive as more extreme objects are found and their orbits are measured. Planet 9, if it is real, would reshape our understanding of the outer solar system. It would mean the planetary census is incomplete. It would mean the architecture of the solar system is more complex than we thought, with a hidden giant orbiting in the cold dark, too far away to have been noticed by any telescope until now. And it would explain a collection of oddities that have been accumulating for years. Objects with orbits that do not make sense, clusters of detached bodies that should not be clustered, a gravitational signature with no visible source, the shadow in the data that grows darker the more closely we look. The search for Planet 9 is ongoing. Telescopes scan the sky, computers sift through images, models refine their predictions, and every year a few more extreme Kuiper Belt objects are discovered, their orbits are measured, and the debate over whether Planet 9 is necessary continues. Some astronomers are convinced, others are skeptical. The data is messy, the statistics are marginal, the sample size is small, but the pattern is there, and patterns in astronomy have a way of pointing toward real things. The orbits of Uranus pointed toward Neptune before anyone saw it. The wobbles in stellar spectra pointed toward exoplanets before anyone imaged them. The clustering of extreme Kuiper Belt object orbits points towards something massive, something distant, and something that should not be there unless we have been drawing the map of the solar system with a blank spot where a planet belongs. If Planet 9 is found, it will not be the end of the story, it will be the beginning of a new one. Because if there is one hidden planet in the outer solar system, there could be others, smaller ones farther out, too faint to detect even with the next generation of telescopes, rogue planets captured by the sun's gravity as they drifted through the galaxy, failed cores that never finished forming. Objects that formed in the scattered disk or the inner Oort cloud and have been orbiting in silence for billions of years, too distant and too dark to show up in any survey. The outer solar system is a wilderness. We have explored the edges of it. We have not explored the interior. And the deeper we look, the more we realize how much we have missed. The fifth lesson, the one that ties all of this together, is about boundaries. The Kuiper Belt forces us to ask a question that sounds simple but turns out to be surprisingly hard to answer. Where does the solar system end? For most of human history, the answer was obvious. The solar system ends at the farthest planet. First it was Saturn, then Uranus, then Neptune, then Pluto, for 76 years until it was reclassified as a dwarf planet and the question became messy again. If the solar system ends at the farthest planet and Pluto is not a planet, does the solar system end at Neptune? That feels wrong. Pluto is still there. Eris is still there. Makmak, Haumea, Quaoar, Sedna, Biden, all of them are still there, orbiting the sun, held by the sun's gravity, part of the same system that includes Earth and Mars and Jupiter. Calling them not part of the solar system just because they are small and far away is arbitrary. So maybe the solar system ends at the edge of the Kuiper Belt. But the Kuiper Belt does not have a sharp edge. It thins out gradually, blending into the scattered disk, which blends into the detached objects, which blend into the inner Oort cloud. There is no clean boundary, no line you can point to and say, this side is the solar system, that side is interstellar space. The transition is gradual, messy, and depends on what you are measuring. If you measure by gravitational influence, the solar system extends to the outer Oort cloud, roughly 2 light-years from the sun, the distance where the sun's gravity becomes weaker than the combined gravitational pull of nearby stars. If you measure by the solar wind, the bubble of charged particles streaming outward from the sun, the solar system ends at the heliopause, about 120 astronomical units away, where the solar wind meets the interstellar medium and stops. If you measure by the population of objects that formed in the protoplanetary disk, the solar system ends somewhere in the scattered disk or the inner Oort cloud, where the last remnants of that disk are drifting in long, slow orbits that will never bring them back to the inner planets. The Kuiper Belt does not solve this question. It complicates it. It adds another layer of structure, another population of objects, another region that has to be accounted for when we try to define what the solar system is and where it stops. And that complication is important because it forces us to admit that the solar system is not a neat package. It is not a row of planets with a clear beginning and a clear end. It is a gradient, a continuum, a structure that starts with the sun and extends outward in layers, each one fainter and more diffuse than the last, until eventually the density of objects drops so low and the distances become so extreme that calling it the solar system feels like a stretch. But it is still there, still orbiting, still still part of the same gravitational system that includes the Earth. The sixth lesson is about exploration. The Kuiper Belt is too large, too faint, and too distant to map completely from Earth. Ground-based telescopes can find the largest objects, the ones that reflect enough sunlight to show up in long-exposure images. Space telescopes can do better, pushing the detection limit down to smaller and fainter objects. But even the best telescopes we have or will have in the next few decades cannot see everything. Most of the Kuiper Belt will remain invisible, known only through statistical models that extrapolate from the objects we can see to the populations we cannot. To really understand the Kuiper Belt, we need to send more spacecraft there, not just flybys, orbiters, landers, sample return missions. Instruments that can sit in the Kuiper Belt for years, measuring the environment, watching objects collide, tracking how the dust evolves, studying the chemistry happening on surfaces that have been exposed to cosmic rays and starlight for billions of years. That kind of exploration is expensive. It takes decades to plan, build, and execute. New Horizons launched in 2006 and reached Pluto in 2015. 9.5 years of travel for a few hours of data collection. A follow-up mission to the Kuiper Belt would take just as long, maybe longer if the target is farther out or requires a more complex trajectory. And even if the mission is approved, funded, and launched tomorrow, the data would not start coming back until the late 2030s at the earliest. Exploration of the outer solar system is slow. It is limited by the speed of our spacecraft, the lifetimes of our instruments, and the budgets of our space agencies. We cannot explore the Kuiper Belt the way we explored the inner solar system, sending multiple missions to multiple targets in quick succession. We will be lucky to visit a handful of objects in the next 50 years, but the payoff is worth it. Every object we visit up close teaches us something we could not learn any other way. Pluto taught us that small icy worlds can be geologically active. Arrokoth taught us how planetesimals form. The next mission, whatever it is, will teach us something new, something we did not predict, something that forces us to revise the models and redraw the map again. That is how exploration works. You go to a place you have never been, you look closely, and you find out you were wrong about something. The Kuiper Belt is full of places we have never been, full of objects that will surprise us if we can get close enough to see them. And every surprise is an opportunity to learn, to refine our understanding, and to ask better questions. The seventh and final lesson is about perspective. The Kuiper Belt is not just a scientific curiosity. It is a reminder of how small we are and how large the universe is. The Earth is a tiny blue dot in the inner solar system, orbiting a star that is one of hundreds of billions in the galaxy, in a galaxy that is one of hundreds of billions in the observable universe. The Kuiper Belt, vast as it is just one small part of one planetary system around one unremarkable star. And yet we have spent decades studying it, building telescopes to see it, launching spacecraft to visit it, arguing over what it means and how it formed, and whether it contains hidden planets or atmospheres on small objects, or clues about the origins of life. We have invested enormous resources into understanding a region of space that is cold, dark, and utterly indifferent to whether we exist. That might sound depressing. It is not. It is exhilarating. Because the fact that we can study the Kuiper Belt at all, that we can send spacecraft across billions of miles and collect data from objects that formed 4.5 billion years ago, that we can measure the orbits of distant bodies and infer the existence of unseen planets and map the structure of a debris field so vast it defies easy comprehension, is a testament to what humans are capable of when we decide something is worth knowing. The Kuiper Belt does not care whether we understand it, but we care. We care enough to build the instruments, launch the missions, and spend years analyzing the data. We care enough to keep looking even when the answers are slow to come and the questions keep multiplying. The solar system is not finished revealing itself. The Kuiper Belt is not finished surprising us. And the search for Planet 9, the hunt for atmospheres on small objects, the effort to map the scattered disk and the inner Oort cloud and the regions beyond, all of it is ongoing. The data is still coming in. New objects are being discovered every year. New models are being built. New missions are being proposed. And every new piece of information adds another detail to the map, another clue about how the solar system formed and evolved and what it looks like now. The cosmic abyss beyond Neptune is not a void, it is full of ice and rock and dust and gas, full of objects we have named and objects we have not, full of chemistry and collisions and slow grinding erosion that has been happening for billions of years and will continue for billions more. It is a wilderness, cold and dark and vast, but it is not empty, it is not silent, it is not dead. It is active, dynamic, and full of stories we are only beginning to read. The Kuiper Belt redefines what the solar system is. It pushes the boundaries outward, from a few billion miles to tens of billions, from a handful of planets to hundreds of thousands of icy worlds. It forces us to think about the solar system not as a neighborhood, but as a frontier, not as a finished structure, but as an evolving system that is still being shaped by gravity, collisions, and the slow march of time. And it reminds us that the map we drew, the one with 8 planets and a neat outer edge at Neptune, was never accurate. It was just the best we could do with the tools we had. Now we have better tools, and the map is changing. The solar system begins at the Sun, a ball of fusing hydrogen 93 million miles from Earth, and extends outward through the rocky planets, through the asteroid belt, through the gas giants and the ice giants, through the Kuiper Belt and the scattered disk and the inner Oort cloud, all the way to the outer Oort cloud, 2 light-years away, where the last remnants of the protoplanetary disk drift in orbits so long and so slow that they will take millions of years to complete. That is our cosmic neighborhood. That is home. Not a row of 8 planets with a few moons and a handful of asteroids. A vast, ancient, dynamic structure full of objects we have barely begun to catalogue, let alone understand. And somewhere out there, in the cold dark beyond Neptune, there are objects we will never name, worlds we will never visit, collisions we will never witness. Chemistry happening on timescales so slow that 1 billion years is a single tick of the clock. The Kuiper Belt is a reminder that the universe does not exist on human timescales. It exists on its own timescales, and those timescales are so long that entire civilizations rise and fall in the blink of an eye. The objects in the Kuiper Belt were there before humans existed. They will be there long after we are gone. And they will keep orbiting, keep colliding, keep grinding themselves down into dust, indifferent to whether anyone is watching. But we are watching. And the fact that we are watching, that we care enough to look, is what makes the Kuiper Belt more than just a collection of frozen rocks at the edge of the solar system. It makes it part of our story. The story of how we came to understand the solar system. The story of how we pushed the boundaries outward, from Earth to the Moon, to the planets, to the Kuiper Belt and beyond. The story of how we took a universe that was vast and indifferent and made it knowable, one object at a time, one measurement at a time, one spacecraft at a time. The cosmic abyss beyond Neptune is terrifying. It is larger than we imagined, darker than we assumed, fuller than we expected. And it is ours, not in the sense that we own it or control it, in the sense that we are the ones looking at it, studying it, trying to understand it. The Kuiper Belt does not need us. But we need it. We need to know what is out there. We need to map the edges of our solar system. We need to understand how it formed, how it evolved, and what it is still capable of becoming. And the Kuiper Belt, vast and cold and strange, is giving us the answers, slowly, one frozen world at a time. So here is what we know. The solar system does not end where we thought it did. It does not stop at Neptune. It does not stop at Pluto. It does not even stop at the edge of the Kuiper Belt, wherever that edge actually is. The boundaries we drew were guesses, placeholders on a map we are still filling in, and every time we look more closely, the map gets larger. Not because the solar system is growing, because we were wrong about how big it was to begin with. 4.5 billion miles wide, hundreds of thousands of objects larger than 100 kilometers across, millions more smaller than that. A total mass that was once tens of Earths before planetary migration and collisions, and billions of years of grinding erosion scattered most of it away. And we have catalogued 2,000 of them. 2,000. We have visited 2 up close. The rest are dots of light in telescopes, faint smudges against the stars, objects we know exist only because they moved when everything else stayed still. That is the Kuiper Belt. A wilderness so vast we will never finish exploring it, so cold that nothing should be able to move,